Start. Sir, good morning and welcome, sir.
Good morning, ma'am.
Morning, sir.
Good morning.
Kirti ma'am, please start the program.
Yes, madam.
Respected chief guests, dignitaries, and all the participants present online today, a happy morning to all. I am D. Vidya Srivani, Assistant Professor in English. On behalf of the Department of Science and Humanities, I take the privilege to welcome you all to the national webinar on innovation aspects for materials science and engineering with reference to intellectual property rights. It is indeed a great opportunity for us to have two excellent personalities as resource persons. One is Dr. K.J. Shankaran, Senior Scientist from CSIR, Institute of Minerals and Materials Technology, Bhubaneswar. Another one is Dr. T. Pavan Kumar, Senior Scientist from the same institute. To begin today's program, I would like to invite Dr. G. Kirti Marita, Faculty of Physics and convener of this webinar, to give her opening remarks. Over to you, ma'am.
Thank you, Vidya. Good morning, one and all. On behalf of University College of Engineering, Adikavi Nanaya University, I welcome all the persons and all the resource persons and the participants to the webinar today. It is a privilege to organize and host today's program. I am happy to have the opportunity to be the convener of this webinar. This event is made possible by the support and encouragement of our Honorable Vice Chancellor, Professor M. Jagannath Rao Garu, and Principal UC Dr. V. Persis Madam. Physics is the basic natural science, studies matter, its motion and behavior through space and time, and the related entities of energy and force. Out of that, materials physics is considered a subset of condensed matter physics and applies fundamental condensed matter concepts to complex multiphase media. Today we are having a eminent speaker, Dr. K.J. Shankaran, Senior Scientist from CSIR, Institute of Minerals and Materials Technology, who will deliver a talk on diamond field electron emitters for microplasma cathode application. And also coming to innovation aspects and IPR, innovation means doing something new that improves a product, process or service. Many innovations can be protected through IPR, the intellectual property rights. Today we are having Dr. T. Pavan Kumar, the senior scientist from CSIR Institutions of Minerals and Materials Technology, to present a talk on innovation aspects and intellectual property rights. I welcome the resource persons to this webinar, and such webinars will help us not just learning of these developments, but also inspire us in new directions in our research and academic pursuits. Nearly 300 participants are here online, sir, and I hope that every participant is benefited from this event. I once again thank you, the resource persons, for their ready acceptance of our request, and we look forward to interesting presentations from them. Thank you one and all. Vidya madam.
Thank you, ma'am. Now I request Mr. M. Balakrishna, Course Coordinator, Department of Science and Humanities, to address. Over to you, sir.
Yeah, thank you. Good morning, all of you. Good morning, respected Vice Chancellor, sir, Chief Guest of the today webinar program, and Princess Madam, Principal University College of Engineering. On behalf of the Department of Science and Humanities, I welcome all the resource persons and the participants. So Department of Science and Humanities is a multidisciplinary department which gives us a unique advantage in the regards interdisciplinary and the transdisciplinary research. So webinar such as these are the part of the university initiative to encourage the academics and the research across the domains of knowledge. This webinar from our department, Science and Humanities, is a series of webinars we are planning in future also. So it is the second webinar. Previous month we organized the emerging trends in engineering mathematics, and also we plans in progress for webinars English in upcoming months. We expect the faculty from our organizations will continue the participation in the future webinars also, and we are very happy that we are very provided with the opportunity to hold such events on such a scale with encouragement from Honorable Vice Chancellor Mokka Jagannath Rao Garu and our Principal Dr. V. Persis Madam. I hope that this webinar will be fruitful experience in discussing and exploring trends, topics in the fields of material science. I wish all the participants a very productive experience. Thank you one and all.
Thank you, sir. Now, I would like to invite Dr. V. Persis, Principal, University College of Engineering, Adhikavi Nannaya University, to speak a few words. Ma'am?
Good morning. Yes, thank you, Vidya. Honorable Vice Chancellor, Professor M. Jagannath Rao Garu, Principal, University College of Arts and Commerce, Professor S. Teki, Principal, University College of Science and Technology, Dr. Ramaneshwari, um, Special Officer, Kakinada Campus, Dr. Kamala, NSS Coordinator, Dr. K. Rani, faculty colleagues of Adhikavi Nannaya University, I'm his Executive Council member, Dr. Jagan Mohan Reddy, convener of this program, Dr. Kirti Marita, course coordinator, Department of Science and Humanities, Mr. Balakrishna, participants and faculty colleagues of University College of Engineering and from other colleges. Good morning. On behalf of the University College of Engineering, I too extend my welcome and I wish to congratulate the convener, Dr. Kirti Marita, for coming up with an interesting and useful theme for this webinar, covering the aspects of innovation and intellectual property rights. As you know, innovation, IPR, incubation, these are all the buzzwords these days. We say that because our future is dependent on this and the country's future is also is driven by these words. So that is the reason we can say that at the center, government is going with many initiatives. You can say that Toycathon students might be knowing that is one such recent initiative focusing on innovation. So I hope that if this, I'm just thinking that if this webinar had happened a bit earlier, even we too might have got some clues to contest for that Toycathon. So hope all the, I wish and hope that all the enthusiastic participants are enlightened and encouraged through this webinar in their move forward towards innovation. And I should mention to the contributions of resource persons, especially Dr. Pavan Kumar. He is familiar with our university. Earlier he addressed us. I too got the opportunity to listen to his address. So today we are happy to have with us both senior scientists from CSIR, Dr. Pavan Kumar and Dr. Shankaran Garu with us. Hope all the participants are benefited through this. And in this context, I want to make an announcement. Many students of Adhikavi Nannaya University are watching this program from the convention center. So I wish to make one announcement that is made by our Honorable Vice Chancellor, who always believes in the innate potential of the students. Sir promised and approved that if any of the students have really good ideas that can be implemented, that are technically feasible, economically viable, and they are struggling for financial support, so necessary financial support will be provided by the university. So this is the promise made by our Honorable Vice Chancellor, and I encourage all the students to utilize these opportunities. If you have idea, see how you can take it forward, how it can add value, how we can make it a process, innovation, and finally how you can protect it through IPR, as Kirti ma'am has mentioned just now. So thank you very much, sir, for your presence today. And I should thank our Vice Chancellor sincerely, because we are here today only because of your constant support and strength, sir. Thank you very much. I thank the organizers for giving me this opportunity. Thank you, everyone. I conclude.
Thank you, ma'am. Now I request Mrs. Y. Sushma, Course Coordinator, Department of Physics, to introduce our chief guest, Honorable Vice Chancellor, Professor M. Jagannath Rao Garu, to the participants.
Thank you, Vidya madam. Good morning, Honorable Vice Chancellor, sir, and good morning, all of you. I am Sushma Priya, Course Coordinator, Department of Physics, University College of Science and Technology. It's my privilege to introduce our Honorable Vice Chancellor, Professor M. Jagannath Rao Garu, as chief guest. Professor M. Jagannath Rao Garu, Honorable Vice Chancellor of Adhikavi Nannaya University, has done his education both in India and abroad. He got his master's degree in engineering from University of Alaska, USA. He got his PhD from Andhra University, Visakhapatnam in the year 1985. He joined as assistant professor in the Department of Geology, Andhra University in 1986, and later promoted to professor and head of the department from the same department. He is a serious researcher and academician having more than 33 years of experience in both teaching and research. He has published nearly 150 papers in national and international journals. 33 scholars got awarded PhDs under his guidance. His students are not only from geology but also from computer science, geoengineering, geophysics, and allied physics. He has strong research collaboration with various organizations from USA, Canada, and Australia. He has completed 8 funded projects from leading funding agencies of this country, including DST, UGC, CSR, DOD, ISRO, and ONGC, etc. He got huge consultancy projects from ONGC, namely studies on Holocene evaluation of Mahanadi Delta, studies on land subsidence due to hydrocarbon exploration and exploitation at KGPG Basin, Andhra Pradesh, using remote sensing and field studies. He has a vast experience in administration. He held various administrative positions like Director for Information Management Center, Andhra University, Visakhapatnam, Dean for PG and Professional Examinations, Andhra University, Director for International Student Affairs, Andhra University, Director for Delta Studies Institute, Andhra University, Chairman for Board of Studies, Department of Geosciences, Ambedkar University, Srikakulam, and Head of the Department of Geology, Andhra University, and many more. He has filed a patent entitled An Inventive Model That Exploits the Genesis of Bay of Bengal and Arabian Sea, which is under consideration. He got many awards and honors, including Dr. Sarvepalli Radhakrishnan Award and the Best Academician Award of the Year 2019 by Andhra University, and also awarded Scientist of the Year 2017 by National Environmental Science Academy, New Delhi. He was in editorial board of Indian Journal of Environment and Eco Planning. He is the member of various professional scientific bodies of national and international repute. He is the NAC accessor and many more. He is a member in various boards of selection committees at national and state level. His earlier selections include UPSC Civil Services Group P examination in 1985, UPSC Geologist examination All India 11th rank in 1983. Because of his passion for teaching, he is in teaching life. His vision is to see that Adikavi Nana University should be the international institute of choice for education, research, training, and consultancy. I am delighted to call upon Professor M. Jagannath Rao Garu to address the participants. Thank you, sir, and thank you for giving me this opportunity.
Thank you, Dr. Sushma, for your nice words of introduction. I'm very happy to be part of this webinar on innovation aspects for materials science and engineering with reference to intellectual property rights. I'm very happy to see all my colleagues here, Dr. Persis, Principal, University College of Engineering, Professor Teki, Principal, College of Arts, Commerce and Management, Dr. Ramaneshwari, Principal, College of Science and Technology, PC member, Dr. Jaganmohan Reddy, NSS coordinator, Dr. KG Arani, Dean CDC and SO, Dr. Kamal Kumari, and the Dr. Balakrishna, and the convener of today's program, Dr. Kirti Marita, and also importantly, the two important resource persons, Dr. KJ Shankaran and Dr. T. Pawan Kumar from CSIR Institute of Minerals and Materials Technology, Bhubaneswar, and all other participants. I'm extremely happy because this is one more webinar in our continuous activity, academic activity where we could explore this platform, online platforms, to see these academic activities continued despite all the limitations of this corona pandemic, whereby we were locked down initially for some time. And I'm very happy all our colleges and all our faculty members are coming forward to see that the academic activity is not stopped. So it's a very good thing, and I congratulate all my faculty and for their commitment towards academics. And I hope this will continue, and in future we'll have more such academic activities. And this is a very, very important topic today, where there is a material science. When you talk about material science, this is the topic of the day. So materials need to be developed for their specific properties, for their specific applications in different fields as such. When you talk about the materials, when you made the materials into nano particles, they have enhanced applications. The research is going on. Materials are being prepared for their applications into biomaterials, into electronic materials, materials used in optical industry, materials that are used in the computational science, ceramics, glasses, composites, polymers, many others. So without materials, there is no application, there is no advancement. Somebody wanted to go to space, we want to make a rocket which should be resistant to these high temperatures that are produced when you're entering back into the earth. So we need such materials which can withstand very, very high temperatures. Similarly, we want materials which need to be used to develop certain things which are medically applicable. Suppose, for example, a stent to be kept in the heart. Similarly, some of the materials which need to be used so that it can be used as a silicon chip. So in this way, materials are everywhere. The materials research is a kind of interdisciplinary research, where the physics and the chemistry and the chemical engineering, the material science engineers will be working together on these materials, which are very interesting properties when they are doped with some other elements, or when they are made into nano-sized particles, or when they are mixed with some other materials. Somebody wanted to have a material which is anti-corrosion, because we want to use these materials when the ships or submarines or any other structures which are there continuously in the sea. So we need to develop such paints which are corrosion resistant. So we need to develop those materials. And similarly, materials which are having a lot of applications in the biotechnology. So it has a sky is the limit. When you talk about these materials, sky is the limit. Being a geologist, I'm very happy that these two resource persons are from an institute where they'll be also working on minerals and also the materials technology. And I also see that there are natural materials which are occurring, like natural ferrites, natural ferrites which are occurring in the form of minerals. Like, for example, as I said earlier also, the iron titanium oxide, ilmenite. So ilmenites are made into nanoparticles. They have excellent properties. So we are working, in fact, we worked with some of these material scientists earlier on to see how these nano-sized natural ferrites will respond to various applications. So in this way, it has immense opportunities, immense the number of opportunity to develop more and more new materials. So in this field, there is a innovation is there. Everybody can think about innovation in developing these new materials. So it is rightly attached to the IPR aspect as well, because when you are developing a new material, you want it to have that to be patented. So what is IPR? What is an intellectual property right? Those things need to be made aware to these youngsters, to these scientists, the junior scientists, and even some other seniors. They do not know, frankly speaking, about what exactly IPR means. So how to go about? So how to uh, have a patent registered? So how the patents are there in Indian patent, an American patent, an Australian patent? How to go about? How much money we need to spend? So are there any opportunities, funding from the government to file a patent? So those things many people do not know. So in this way, an expert like Dr. Pawan Kumar, who will be speaking about on the IPR, it's the greatest opportunity for all the youngsters to know how to go about, because many people, many scientists, they are working hard, they are publishing papers. Sometimes those are actually can be patented. So before you publish, you need to patent that, so that an idea you can patent, and a device can be patented, a model can be patented. So once you patent, there may be an opportunity for you to commercialize as a commercial application. So once it is having a commercial application, then you can claim some part of the revenue derived from obtained from that the material which is having industrial application, or the device having industrial application. So first of all, we should know what are these regulations of IPR, what is a patent, how to go about all these things. Our youngsters should know. As Dr. Persis said, we need to use all these youngsters. We need to drive them towards thinking about out-of-box thinking. What is to be developed, because it's not learning something theory in the classroom. We need to inculcate that kind of thinking among youngsters. Then only they will come up with some kind of new models, new devices. They should think out of box. It is not simply teaching them from the textbooks. You need to use their energy. We need to see that their original ideas flourish. We should not discourage them. Sometimes the students will come up with some idea. We should not discourage them, even if it is not logical, maybe it's illogical, but still let them think. Let them think originally. Let them come out with something new. So that kind of attitude and scientific temper should be inculcated among the students. We should not discourage them. So we should encourage them by having some platforms like clubs of innovation, where, as Dr. Pitts already indicated, we are here to support the students who are coming with something new or some innovative ideas. As an individual or a group of students, or working with their faculty, let them have such platform in this campus. Let us see really these engineers, the budding engineers and scientists of this campus will be thinking out of box, will come up something new. That will be a kind of starting point for these youngsters to become a real innovators, a real scientists who will be contributing immensely to this country. Because as we know, we are producing number of PhDs, number of graduates, but when you see at international level, the percentage of our patents from this country are far below, far less than many other countries. For example, when you compare with China. So we are no less than, our scientists are no less than the Chinese scientists, but that kind of awareness, that kind of encouragement is to be there, is to be established in this country. Once again, I congratulate the Department of Science and Humanities for organizing such a wonderful webinar on this material science as well as IPR. And also I thank our speakers today, Dr. Shankaran and Dr. Pawan Kumar, for accepting our invitation and for participating in this webinar. I'm very sure that all our youngsters and participants in this webinar will be benefited by their experience and expertise. Thank you. Thank you very much.
Thank you, sir. Now I request Dr. G. Venkat Rao, Assistant Professor in Mathematics, to introduce our first speaker, Dr. K.J. Shankaran.
Thank you, Vidya Madam. Dr. K.J. Shankaran did his PhD in Material Science and Engineering in 2013 from National Tsinghua Huai University in Taiwan. He was a postdoctoral researcher from 2014 to 19 at Hasselt University in Belgium. He has published over 90 papers and 2 book chapters. He has received Best Oral Presentation and Best Poster Presentation Award from International Symposium on Thin Films and Coatings, Taiwan in 2013 and 14. He has received many awards, including the Outstanding PhD Scholarship Award from National Tsinghua Huai University, Taiwan in 2010. Dr. K.J. Shankaran is currently working in CSIR Institute of Minerals and Materials Technology as Senior Scientist at Bhubaneswar, Odisha. On behalf of Department of University and Department of Science and Humanity and University College of Adhikavi Nanna University, we welcome to our webinar, sir. Sir.
Good morning, sir.
Good morning, sir.
Sir, can you hear me? And can you see my slides there?
Yes, sir.
Yes, sir. So it's in full screen now?
Yes, sir.
Okay, sir. Okay, sir. So good morning, everyone. And thank you for your kind invitation to present my work here. And thank you, VC sir, for giving us a very good introduction about the materials and how it's working for the intellectual property rights. So basically, I'm Shankaran, a senior scientist from CSIR Institute of Minerals and Materials Technology, Bhubaneswar. So today I'm going to discuss about the field electron emission from diamond for especially for microplasma cathode applications. From our Indian community, research communities, diamond is a very old material, but the growth of diamond in India is very less because it needs some expensive and also some sophisticated tools to fabricate the diamond materials. But the applications of diamond are really huge. We can apply the diamond in so many applications from our Indian. Am I audible, sir?
Yes, sir.
Okay. So there are so many applications in the diamond based on the electronics and the electrochemistry and also in sensing applications. But my area is in the field electron emission based devices from diamond, and we apply these diamond field emitters for the microplasma cathode applications. So before going to my talk, I would like to introduce about my institute, CSIR Institute of Minerals and Materials Technology. So this is our very beautiful campus in the exactly at the middle of Bhubaneswar, and so green environment compared with the other CSIR institutes. Even in the center of Bhubaneswar, you can see such a very beautiful campus. So I would like to invite you all to come over here for some research collaboration as well as for some project dissertation works. We are very happy to invite you people here, and basically we are working on this departments. I belongs to the Advanced Materials Technology department, and we have a very good centralized characterization technique unit with all characterization instruments, like starting from microscopies like SCM, TEM, advanced force microscopy, and for the other characterization instrument like XRD, FTAR, XRF, TGDTA, like etc. So we have all kind of central characterization techniques in our institute to know the properties as well as the applications of your synthesis material. So as I mentioned, I belongs to the advanced material technology department, and these are our research activities ongoing in our department. So I belongs to the processing of minerals, waste, and special materials using the plasma treatment. And there is other works also based on some metallurgical oriental like metals and alloy making. This is a very interesting work one of our colleagues are doing. They are working on these metals and alloy makings for these flight aircrafts. And also there is a group they are working on the carbide oxide and nitride powders. Also they are working on some thin films using some RF sputtering technique. Those can be used for some thermoelectric materials. So I belongs to the plasma processing of minerals, waste, and special materials. The special materials include diamond like carbon, also some metal and metal oxide thin films for electron emission, as well as some electrochemistry and some sensing applications. So this is the basic outline of my talk. In the introduction part, I would like to introduce about what is carbon. Since the students are here more, I would like to tell about the basics, how we are synthesizing the diamond materials. So starting from the carbon and the allotropes of carbon, and then continue with the diamond and how we are fabricating the diamond materials. So I'm sure that you will have experience like you are doing the diamond growth by virtually you are going to do the diamond growth with me. So here I mentioned about the diamond hybrids. The reason is that as the diamond is a wide bandgap material like more than 5 EV, so we need to hybrid this material with other conducting materials.
Excuse
so that
me,
sir.
Sir, sorry to interrupt you, sir. Sir,
Yes,
I
sir.
think there is a pause in the screen sharing, sir. Only the title slide has been displayed so
Is it
far.
moving, sir?
No, sir, it's not moving, sir. Would you be kind enough to share it again, sir?
Yes, sir, I'm doing again. Sir, is it okay, sir? Now you are seeing the outline slide?
Yes, sir. And it's not full screen, sir.
Yes, sir. Now is it fine, sir?
It's not full screen, sir, yet.
Sir, 1 minute, sir. So actually, I have made into full screen and then share the screen.
Okay. Sir, after sharing the screen, just press F5, sir. It should be full screen.
Okay, sir. So is it full screen, sir, now?
Just a second, sir. Give it a second, sir. It should.
Sir, is it full screen now?
No, sir, not yet. Not yet.
Shankar,
Yes,
Shankar,
sir. Yes,
Shankar,
sir.
I'm Pawan. I think you have to share it. After sharing, you please do full screening.
Okay. Yeah.
That would
Okay,
be fine.
Yes, sir.
So now I'm sharing now,
Yes,
and
sir.
then
Yeah.
I'll make to full screen.
Yes, you do it.
Is it okay?
You are doing, but I think it has not come yet.
But for me, it's showing full screen here.
Sometimes, otherwise, just you de-share and again share it.
Yeah, I did the same actually. So are you seeing my screen now?
Sir, I'll try to.
Sir, are you?
Raghu, sir. Sankaran sir, co-host event, sir. Sankaran sir, Dr. KJ Sankaran sir. Sir, we are giving the co-host privileges, sir. That should enable you to share the full screen.
Okay, sir.
Just just try it once again, sir.
Okay, sir. Now I'm doing the share screen application window. I'm selecting my PowerPoint.
Yes, sir.
And then share.
Yes, sir.
So is it appear, sir, now?
It is appear, sir.
So now I'm making full screen.
Yes, sir. Plus F5, sir.
Yes. F5. Is it appear, sir?
No, sir. It is still still showing as a slide.
But for me, it's showing full screen, sir. I don't know. It's showing me the full screen here.
Or you, Shankar, you try again. Otherwise, you yourself make full screen and share it. We'll try in that way.
Yeah. That's why I
Sometimes
can.
these technical glitches are there.
Yes,
Okay,
sir, yes.
yeah.
No need to worry. Yeah.
Yeah. I made full screen. But the problem is if I make the full screen, how I can go to the app again?
It's the Windows key, sir.
Shankar, I think there you have to minimize your screen. From there you have to share so that you can directly share the full screen.
Press the Windows key, sir. You should be able to see the Windows bar.
Okay, sir. Yes, sir.
And select the Zoom one, sir, and start sharing the full screen version of PowerPoint, sir.
Is it okay, sir, now?
Yes,
right.
Yes, right.
Okay. So is it
Thank you.
moving? I'm going to the next slide. Is it moving?
You just
Yes,
try.
Try, sir. Yes,
Yes. Perfect. Right.
Okay. Okay,
Right.
sir.
Thank you so much, sir.
Okay, sir.
Sorry for the inconvenience.
Yeah. I'm sorry for that. Okay, sir. So I'll start from the introduction slide of CSIR IoT. So basically, we are CSIR, Institute of Minerals and Materials Technology, Bhubaneswar, and these are the departments in our IMMT. And I belongs to the Advanced Materials Technology department. So these are our research activities in our department. So I belongs to the plasma processing of minerals, waste and special materials. The space materials includes diamond like carbon, and metal and metal oxide thin films for electronics, electrochemical and sensing applications. So this is the basic outline of my talk. Sir, is the slides moving now? I'm in the outline slide.
Yes, sir.
Okay, ma'am. Yeah. So in the introduction part, I will introduce about what is diamond and how we are synthesizing the diamond. And I'm sure that you can, the students can come with me to know how we are growing the diamond in a virtual way. And also in the diamond hybrids, we will. I would like to show the fabrication of the diamond and how we are making the diamond combination with the other hybrid materials like graphene and carbon nanotubes to get a highly efficient field electron emission characteristics as well as the plasma illumination. And finally, I summarize my talk. So this is the nothing but this carbon that when we are cooking in our home, when you are using with the some wooden things, with a very old technique of cooking. From the wooden one, you see at the pot, we'll see the black color one. So this is that carbon particles that we collected in the hand, and this is also the coal. So this form of materials is the carbon, and it has the atomic number of 6 with a electronic configuration of 2s square and 2p2, and you can see that carbon which have many states like free state and combined state. I'm not going to talk about the inorganic and the organic way of carbon. I will focus on the crystalline and the amorphous phases. So in the crystalline, you can see graphite, diamond and fullerenes, and my work is mostly based on the diamond as well as also combined with the, not actually the graphite is a graphene, is a one-dimensional nature of a graphite. So on combination with the diamond and the graphene, how we are efficiently making field electron emission devices, especially for the microplasma applications. So as you can see here, these are the allotropes of carbon like sp3, which is for diamond of this being of 0.154 nanometer, and you can see this is sp2, this is graphite of this spacing of 0.142 nanometer, and you can see this is bonding with the hexagonal, which is bonding with van der Waals bonding, and this is C60 fullerene balls and C70 of a carbon nanotubes or something like a tube-like structures. But we can get more allotropes of carbon. So there is only one same atom, the same carbon atom, which have different properties based on the different hybridization. That depends on the orientation and the hybridization. So if a carbon material can vary with properties, that depends on the orientation and the hybridization of that carbon material. So today I'm going to talk about the diamond, but as we all know that is a very precious stone in the jewelry, is the very costliest one as well. And these are the single crystal diamond that can be used for the ornamentals one. But I'm not going to talk about the diamond, about the use in jewelry. I'm going to talk about the other face of diamond, which can be used in various applications, especially as a hard coating, because it's the hardest known material in the world, and it can be used as a hard coatings in grinding, polishing. That can be used as a hard coatings in the drill bits, cutting tools, and dicing saws. Also, it is a very good wide gap material for the high power electronics, heat sinks, and radiation detectors. And diamond in chemical way, it is inert to acids, bases, and other chemicals. So these properties makes diamond in a very huge applications. But only thing is that we need to optimize the growth conditions of the diamond to be applicable to use in all kind of these devices. So this is the crystal structure of diamond, and you can see the animated one of the diamond, which is a face-centered cubic structure with a lattice constant of 3.5 Armstrong, and it has a very good atomic density of 1.77 10 power 23, so that per centimeter cube, so that it's a very, because of this very high atomic density, it is a very hardest known material. And here I introduce some of the properties of diamond. I mentioned this is the very hardest known material, and especially for the electronic applications, I need to focus on the band gap and the resistivity. So the band gap of diamond is 5.47 eV. So it's a wide band gap material. So you can see it's very difficult to conduct the electrons through the diamond material because of the wide band gap. So you can see the resistivity is really very huge, of greater than 10 power 16. So since the diamond is highly insulating material, my work needs conducting diamond. So how we can make conducting diamond using a different synthesis method. So I'm going to show about those, what are the methods people are following to synthesize the diamond. But before going to that synthesis method, like a synthetic diamond, I need to focus on how natural diamond be produced in the earth. So there are 4 methods that we can achieve the natural diamond. So the one you can see is the deep shores eruption, another is the asteroid impact, and the third is the subduction zone, and the fourth one is the meteorite fall. So if you dig the earth for around 150 to 200 kilometers, and there occurs a high temperature as well as a high pressure. So if you have a coal in the earth crust of around 150 to 200 kilometers, there achieves a high temperature and high pressure, that helps us to get the natural diamond. So the condition to get the diamond is a high temperature and the high pressure. So these 2 conditions are really important to synthesize the diamond. So these are the diamond mines in Africa. You can see how big is that, and how people are getting the diamond mines in Africa. I would suggest you people to watch a very good Academy Award movie, Blood Diamond. There you can know, come to know that how difficulty is that to get a small piece like a 1 carat of diamond. How people are suffering in the diamond mines. Basically, it's movie focused with the Belgium colony in Africa, and the guy who got a small piece of diamond, and how it's a valid one, because they are suffering a lot to get a small piece of diamond. So you will understand why diamond is so expensive if you watch this movie. So it's really very expensive, so that it's very difficult to get the natural diamond in the diamond mines. So people start to synthesize the diamond using artificial method. So we look for the artificial method. As you see that to grow the artificial diamond films, we need to know 2 methods people have used: high pressure and the high temperature method, and the chemical vapor deposition method. Before going to that, I would like to mention what is film. What is film? That is called a thin film growth. Basically, as a small example, as the girls, they will use the nail polish in their fingers on the nails, so that if you see that, you see such a small like a film that is covered on your nails. So sometimes we can also peel it off from your nails. So you can see like a very freestanding film on your hand. That may be in a micron size. So that is like a thin film. So those kind of thin films we are growing in different methods like chemical vapor deposition methods, sputtering techniques to on some different substrates to achieve a very good adhesion on those substrates, that the thin film can be grown on those substrates. So for the diamond films, I would like to focus on the two methods. One is the HPHT and the CVD method. As you see in the HPHT, this is the HPHT method. There you can see it needs a really a high pressure as well as a high temperature. The similar like the one people are getting the diamond in natural way. So we need to use the same condition how people are getting in the natural diamond way, like the high pressure and the high temperature. But you can see the CVD technique. It needs only a less temperature and also a less pressure. So CVD techniques are the really advantage one compared with the HPHT to get a very uniform diamond growth as compared to the natural diamond. So there are two CVD methods, well-known one, that of the hot filament CVD and the microwave plasma CVD. So coming to the hot filament CVD, you can see the hot filament here, which is of tungsten filament that can be heated up to more than 1000 degrees Celsius, so that once you pass the gases, this high temperature filament can emit some electron that can react with these gases and make it plasma, so that it can make a film on the substrate. This is the substrate heater and this is the substrate, so the diamond can be grown on the substrate. But when you go to the microwave plasma CVD, it needs a very low pressure and also a very low temperature, because when you inject the microwave to the system, once past the gases, this microwave reacts with the gases and can make some species, that is the reactive species or the ionic material or the radicals that will form as a plasma ball. So this is the plasma ball that can react with the substrate, can form as a film on the substrates. So basically microwave plasma CVD is more advantageous than the hot filament CVD, because the hot filament that we are using is we need to replace the hot filament many times, even for a growth, if you are looking for a very thick diamond films. So microwave plasma CVD is the best method as compared to the hot filament CVD and other CVD techniques. So there are many microwave plasma CVD techniques, and compared like a microwave, DC plasma, combustion flame, linear antenna, and electron cyclotron resonance microwave plasma. One thing I want to focus is the linear antenna CVD. This linear antenna CVD is the recent made CVD that came in 2015, and we can grow diamond films as like a big size pizza. So if you have a big size like a 8-inch silicon wafer, we can achieve a very uniform diamond film using this linear antenna system. So it's like the system looks like a pizza machine, and we can put a pizza tray, that is your substrate, and we can get a very nice diamond pizza that's formed as a diamond film on your silicon substrate. So this is the more advantageous microwave plasma CVD recently made by the experts. So now I'm going to the diamond film growth, how we are growing the diamond film. So these are the silicon substrate that we commercially available one, and we need to make a nano diamond seeding. Why we need the nano diamond seeding? Because silicon substrates can be used mostly for the microelectronic devices, and then if you use the diamond film on this silicon, it has a very good adhesion property between diamond and silicon because of the low thermal mismatch. So that adhesion is very good between the diamond film and the silicon. But silicon don't have any diamond on its surface. So we need to seed the nano diamond particles on the silicon substrate. So these are the nano diamond particles commercially available, with a particle size of 5 to 10 nanometer sizes, and we'll make us a nano diamond colloids with suspension with a distilled water, and so that this is the nano diamond colloids. So then we drop those nano diamond colloids in a spin coater machine. So this is the silicon substrate, and some drops of silicon nano diamond colloids are placed on the silicon substrate. So once spin coated, you can see that the nano diamond seeds were placed on the silicon substrate. So here I mentioned use the 100 substrate. If you use different phases of silicon substrates, that we can get different planes of diamond, but we are growing mostly with the polycrystalline diamond materials, not the single crystalline diamond. So these are the silicon substrate which is seeded with the diamond seeds. So then what we'll do is that this is the microwave plasma CVD. It is a very big system, near to around 7 feet of system, and this is the schematic diagram of this microwave plasma CVD system. And this is the chamber that we need to place our silicon substrate. So you can see once you open this chamber, you can see there's the inside part of the chamber, and we need to keep this seeded silicon substrate in a substrate holder. So this substrate holder will be placed here, and then we close the chamber and start pumping to create vacuum. The vacuum should be in the level of 10⁻⁻⁶, so that there won't be any contamination in the diamond film growth. So this vacuum system, this diamond films, if you need a high quality, should be in a high vacuum like more than 10⁻⁻⁶, so that we will achieve a high quality diamond films. So once you close this chamber, we create vacuum, and then we start growing the diamond films by passing the gases, like different gases. We can use it for different applications of diamond, and then we can use the microwave. So once microwave pass through the chamber at a particular pressure and particular temperature, you can see a very uniform plasma that forms over the substrate holder. So this is the plasma that formed on the substrate holder, which have the silicon substrate here. Depends on the gases that we are using in the growth, that are the process gases that we are using, we can achieve different colors of plasma. So this is the diamond film after the growth on silicon substrate. So this is the silicon substrate, which is unseeded one, and after the growth. So you can see a darkish bluish color of diamond films on the silicon substrate. As I mentioned, different colors of plasma which give results in a different morphologies. So what are the different colors of plasma with different process gases? Here I show a very detailed list of different colors of plasma. You can see that when you use hydrogen and methane of ratios 99:1, we'll get a violet colored plasma that I have shown in the earlier slides. And when you use only methane and CO2, the plasma colors varies a lot. In the middle, it looks like a blue, yellow, and the bottom would like a violet one, and the top will have a orange halo. And you use one methane and argon, it becomes like a brighter greenish region. It's a very big plasma as compared to the hydrogen plasma. And when you go for only with CO2, it becomes like a bluish white. And only with methane, it becomes like a bright white center having a extended orange at the corners. So different plasma colors will achieve with different gases. So different plasmas will result in different morphologies of diamond. You can see that when you use methane and hydrogen plasma, it results in a microcrystalline diamond. We call it as a MCD. Why we call it as MCD? The reason is that this grain size of diamond is 5 micrometer. So this is the pink plasma I have shown earlier, the purple like plasma. And when you incorporate argon in the methane and hydrogen, what happens is that the grain size from micron size will change to a nano size. So what happened if you remove the hydrogen from methane and argon? There's a big change is that it become ultra nanocrystalline diamond. Why we call as ultra nanocrystalline diamond is that the grain size becomes less than 10 nanometer and a very smooth surface. The roughness is really very less than 5 nanometer. And this is the whitish green plasma is a very big plasma because argon will dissociate into methane and makes a very big plasma. But the dissociation of hydrogen with the methane is very less, and but this is very strong plasma. This is not that much strong, so that the dissociation of methane convert to C2 and CH3 species. So C2 helps to grow on this UNCD. So ultra nanocrystalline diamond films having the grain sizes of really less than 10 nanometer compared with the microcrystalline diamond. These UNCD films are very, very smooth in nature, and you can see this like a very big rocks of 5 micrometers. So the roughness is really very huge. So depends on the applications, we can use different morphologies of diamond. So we can use the diamond materials for various applications, especially for the micro electromechanical systems. This is for the microelectronic devices that can make the radio frequency resonators, and UNCD probes. They were coated the UNCD films on these tips and also some 3D structures. So this is the UNCD, very uniform UNCD film wafers that can be used for some electronic applications. And because of the very smooth surface of UNCD, it can be used for coatings. So uniform coatings can be achieved on some wear bearings. And yes, a very big project is going on in US Argonne National Lab. They are working on this UNCD artificial retina project. So they have coated a conformal uniform coating on silicon microelectrode. So they would like to use in a retina to make an artificial retina. This project is still running in the Argonne National Lab, and we can also use these diamond films in a surface acoustic wave devices. This can be used in spacecrafts and also in some satellites. And mine is focusing on the field electron emission devices. So this is the field electron emission display device, commercially available one. So we can coat the diamond on any nanostructures so that we can achieve a very good field electron emission from the diamond materials. So I will focus on the field electron emission devices based on the diamond materials. So before going to the application of diamond in the field electron emission, we need to know what is field electron emission. So basically, field electron emission is the emission of electrons from the surface of a material due to a high electric field. It's a very simple mechanism follows. One is the transmission of electrons. So it's called as a quantum tunneling. So the electrons can pass through a potential barrier inside a material with a work function of pi. So this barrier need to be optimized so that we can achieve a very good transmission of electrons in the material. And finally is the supply of electrons from the bulk material to the emitting surface in the vacuum. So the two mechanisms happens. One is the transmission of electrons, another is the supply of electrons through the quantum tunneling way. So the emission of electrons from the surface of a material due to a high electric field. So what we'll do is that we'll supply a high voltage to a material so that electrons will emit from the material and emit in the vacuum. So we'll collect the electrons that will be used for the electron emission displays. So this is the field electron emission setup. It's a schematic diagram which contains an anode and a cathode. The cathode, we use the sample, that is the diamond coated on the silicon, and the anode which having a tip, very sharp tip of around 2 mm with this made up of a molybdenum material. So this field electron emission setup which the experiments will be carried out in 10⁻⁻⁶ star. So these are the results we achieved from the field electron emission measurements. This is the current density versus the applied field. How we are getting we followed a Fourier Nottingham model to obtain this current density versus the applied field. Once you supply the voltage to the cathode, the electrons will start emitting, but it won't emit with a at a particular voltage. It starts to having a threshold voltage here. So this point is the threshold voltage. To know accuracy where the threshold voltage occurs, there is another form of the Fourier Nottingham model, that is the Fourier Nottingham plot. So this is the FN plot. So this FN plot, which is derived from the current density versus the applied field, and from this FN plot, the intersection of the high field segment and the low field segment, which provides you the threshold voltage, though we call also as a turn-on field. So the turn-on field means is that at a particular voltage, the electron starts emitting. So this is no emission of electrons. Here it starts a continuous emission of electrons. So we can determine the turn-on field. So the turn-on field should be very less so that we no need to apply a high voltage to a material. So we need to study how diamond films having the behavior in the field electron emission. Also, from the FN plot, we can also calculate the field enhancement factor. So the field enhancement factor is a beta factor which can be obtained from the electric field at the emitter tip versus divided by the voltage between the anode and the cathode. So this field enhancement factor, which will be improved if you are having a nanostructuring of your material. So I will also explain about the field enhancement factor in my work. So these are the various applications of the field electron emission materials. So we can use the field electron emitter as in a vacuum microelectronic devices as a cathode material, and in a flat panel display also as a cathode in a micro sensors as well as in a cold cathode emitter. And recently people are using these emitters as a probe in a scanning probe microscopy for surface imaging. It's like in AFM we'll use a small tip like a silicon tip. People are using the diamond coated silicon that will try to extract the surface imaging from your material. So we can also use as a probe using these field electron emission materials. So these are the flat panel displays that commercially available one. And this is the Motorola. They have designed the flat panel display using the digital one. You can see with various. These are the phosphor screens, and these are different colors from the Motorola. They have designed using the flat panel display by using carbon nanotubes as the emitter, not the diamond. So to be as a very good field electron emission cathode material, here I list out some of the requirements of a material. So the material should have a low onset field, that is the low tenon field, and it should have a low surface overfunction, high robustness, resistance upon ion bombardment, long lasting stability, stable emission current. So based on these achievements of a material, we can utilize this material in a field electron emission. People have used so many materials. Out of that, carbon nanotubes, zinc oxide nanorods, and graphene, they produce a very low onset field. These are the very famous very famous field electron emission materials that can go for their real applications. But there are many drawbacks from these materials. The drawbacks is that you can see that carbon nanotubes, it can emit the electron with low tenon field. Also with the graphene, you can see the tenon field is nearly around 2, but it can achieve low onset field and low surface work function. But these materials have some drawback in other way, like if you have a 360 volt applied voltage to a CNT, you cannot see a very uniform emission. And once you apply a high voltage, it start arcing, so the material is completely damaged. So, and also the long lasting stability with stable emission current, you can see that it cannot last for a longer time, only up to 30 minutes. So for a device applications, this lifetime is really a nothing. So we need a long lifetime stability. And coming to the graphene nanoflags, this is the 0 seconds at here, and after 500 seconds, you can see these graphene nanoflags were completely etched out in the plasma environment. So it cannot last, it cannot stable even nearly around 250 seconds. After that, the current starts to decay. So we need a stable emission current with long lasting stability and also a high robustness with resistance upon ion bombardment, that is in a plasma environment, if you are looking for a microplasma applications. So what we can do to achieve these properties to have a better field electron emission application? We can use the diamond films, but I have mentioned already diamond films have wide band gap and high resistivity. Then how diamond can be used in field electron emission? There are some special properties of diamond. There we can use this diamond, which is more advantageous in the field electron emission devices. The main one is the high thermal conductivity, chemically inert nature, and small effective work function. These properties of diamond really help that we can use this material in a field electron emission, because as a chemically inert nature, it will be a really robust material and in any harsh environment, and a small effective work function, which helps this diamond to achieve a low threshold voltage similar to the carbon nanotubes or graphene. So we can use these diamond films for field electron emission. So here I compared the field electron emission results with the UNCD as well as the MCD. The UNCD I have mentioned is the ultra nanocrystalline diamond with a smooth surface and very small grains, and the microcrystalline diamond with bigger grains of sizes 5 micrometer. So compared with this UNCD and MCD, you can see that UNCD shows a very good field electron emission, showing a turn-on field of lowest one as 19.7. But MCD having a high turn-on field of 65. So it has a very high turn-on field. But UNCD has a very low turn-on field and also a high current density of nearly around 1.04 milliamp per centimeter square. But MCD having a very low current density. To know the reason, now we achieved UNCD is much better than the MCD in field electron emission. To know the reason why UNCD is better than MCD, we need to characterize the material. What we already mentioned, the characterization tools are really important to know the properties of a material and to know the reason why that material is really efficient in nature. So there are many characterization tools available to know the properties of the material. So to know the reason why UNCD is much better than the MCD, I would like to go for the transmission electron microscopy because I have shown the scanning electron microscopy. This one shows only the surface morphology, and we can find it has a very less roughness, and also a smooth structure with very small grains. But we don't know what is interior in this UNCD. That we need to find the microstructure. So the microstructure of this UNCD can be found only by the transmission electron microscopy. So this is the transmission electron microscopy that I was working in Taiwan for 2 years. After my PhD as a postdoc in Taiwan, I was operating this TEM. So to get one very good TEM image, you need to spend the time because the sample preparation for TEM is a very big job. One sample we can prepare one sample in a week, and to categorize this sample in the TEM is also a big task because focusing the material to get a very good image is not an easy one. So we need to spend much time and we need more patience and hard work to get a one single image of very good image from TEM. So here I show the TEM image of UNCD that is grown on the silicon. So this is the bright field TEM image of scale of around 20 nanometer, and this is the selective area diffraction pattern that we achieved from this bright field TEM image. There you can see that it has a diffraction rings 111, 220, and 311, which confirms there is a polycrystalline diamond nature. This is like the diffraction pattern how we are getting from the X-ray diffraction. And this is the high resolution TEM image acquired from this bright field image. So this is the magnified image of this image. So this magnified image shows that this is a diamond grain of nearly 5 nanometer scale, and surrounding these diamond grains we can see there is some other phases there. You can see the Fourier transform images acquired from this high resolution image. So the number 1 shows the small diamond particle, and this is the Fourier transform image which represents the formation of diamond here. Very small ultra nano sized diamond grains, and in the grain boundaries between these two diamond grains we can see amorphous carbon phases. So these amorphous carbon phases exist between these two diamond grains. So this is a diamond grain and these are the grain boundaries that presents in the UNCD films. So this presence of amorphous carbon in the grain boundaries, what happened is that there is a very easy grain boundary conduction mechanism because these amorphous carbon in the grain boundaries which helps for the electron transport. So the transport of electrons and the supply of electrons from the bulk material from the bottom to the top portion, which is very easy if you have the amorphous carbon. But if you do see the MCD, there is bigger grains which less amount of amorphous carbon, and this having an aspect ratio of very less. But this is UNCD grains of spherical nature. It has the high aspect ratio, so that electron emission will be enhanced, which shows a very good current density. So UNCD is much better than the MCD because of the presence of amorphous carbon in the grain boundaries. So this mechanism is the grain boundary conduction mechanism. But there is also a drawback for the UNCD because the presence of amorphous carbon in the grain boundaries is also not conducting enough. This is also one of the drawback in the UNCD because that amorphous carbon hinders the transport of the electrons from the in the UNCD films. So how we can make the UNCD films highly conducting? So we would like to improve the field electron emission of UNCD films following by 2 methods. One is the incorporation of the nitrogen in the plasma because these UNCD films were grown in methane and argon plasma. And another method is the gold ion implantation. So first I'll start with the incorporation of the nitrogen in the plasma. So as I mentioned again, I'm mentioning again, methane and argon plasma grown UNCD films are highly insulating. Even though in presence of amorphous carbon, they are not highly conducting. So we cannot use those UNCD films in some field electron emission devices. So the UNCD films grown in methane and argon plasma, I'm going to replace this methane argon into methane and nitrogen. So what happens in this methane and nitrogen plasma? Here you can see that the UNCD films with spherical grains converted to a nitrogen UNCD with wire-like structures. So a big change in the morphology occurs, but this changes occurs which took me 2 years. So by optimization of the growth conditions of UNCD from methane and argon to methane and nitrogen, I just say easily like methane argon to methane nitrogen. But we need to optimize the growth conditions in terms of pressure, microwave power, gas conditions like the flow rate of the gases of methane and nitrogen composition, and also the substrate temperature and the distance between the substrate to the plasma. So these many parameters to be optimized to achieve this perfect NUNCD wire-like morphological diamond films. So it took 2 years for me to get this NUNCD films. So as a researcher, so the students, if you want to go for research in the future, what I learned from my experience, we need patience and hard work that will help us to achieve a very good material. And the system what you are using, you need to be friendly to the system, so that that system will also be friendly to you, so that you can get a very good material from the system. So you need to give some dedication, hard work, and then patience to get a very good material. So how these NUNCDs are better than the UNCD? We did the field electron emission measurements, and you can see that NUNCD having the low turn-on field and a high current density as compared to the UNCD, which have a turn-on field of really 19. So again, the question arises, why NUNCD is much better than the UNCD? So we need to know again the microstructure of the NUNCD. What is the reason? So also to know localized field electron emission studies using scanning tunneling microscopy and the scanning tunneling spectroscopy. This is a very sophisticated tool that we measured in 10⁻⁶ torr in a high vacuum environment to know the localized electron emission. So we can see locally that maybe in a very nano sized region, we can see where the electrons are emitting from the grains or maybe in the grain boundaries. So G represents the grain and GB represents the grain boundary for this particular AFM image. And you can see that the grains, which is a dark region, and the grain boundary is the red region. So the red region represents the electrons are emitting from that region, and the black region shows there is no emission. So if you see from the tunneling current for the supply of voltage, you can see that the grain boundaries which emitted electrons with a low supply voltage compared to the grains. So also the grain boundary shows band gap in a metallic in nature, but the grains of 5.5 EV, which represents the grains are diamond in nature. So what is in the grain boundaries? In UNCD, we found amorphous carbon, but what is in the NUNCD grain boundaries? So that you like the TEM, to take the TEM. From the TEM image, this is the one single diamond nanowire as you see in the SEM morphology, and the covering with these diamond nanowires, we can see there are many waves like structure. Those are the graphitic phases. How to confirm this is graphite? So this is the colored high resolution TEM image, and you can find this is the diamond nanowire. The yellow color region is the diamond nanowire, and the green regions, those shows the graphitic phases. These graphitic phases are really conducting in nature as compared to the diamond, because this is sp2 hybridization and diamond is the sp3 hybridization. Now with the d-spacing of diamond is 0.21, which is taken from this region, and the F region shows from this region we took the d-spacing of 0.34, which represents the sp2 graphitic phases. So the presence of graphitic phases in the grain boundaries, as well as the one-dimensional wire-like morphological nature, which help to emit the electrons very easily, that makes a conducting diamond for for the nitrogen doped ultra nanocrystalline diamond films. So the presence of nanographites as the grain boundaries makes the films more conducting compared with the amorphous carbon, and also the one-dimensional nanowire like morphology, which improves the aspect ratios, which makes NUNCD films conducting in nature with efficient electron emission. Here so far I have shown only the flat films with wire-like morphology. But can we make one-dimensional nanostructures? So following slide shows that how to make the NUNCD nanorods. Here we have grown the NUNCD flames with wire-like morphology. And then what we are doing is that we are going to mask this NUNCD flames using nanodiamond powder with deionized water. So those masking which happens by the ultrasonication method, and then we follow the reactive ion etching process using oxygen and CF4 plasma. So these NUNCD films masked with the nanodiamond particles will be placed here, and oxygen and CF4 gases will be passed, which creates a plasma, so that while etching, so this oxygen and CF4 plasma makes a etching on your substrates, that is the nanodiamond coated NUNCD films. And then after etching for 30 minutes, you can see a vertically aligned NUNCD nanorods of around 700 nanometer in length and 50 to 60 nanometer in diameter. So this is a very uniform NUNCD nanorods that formed on the NUNCD films. If you look at the field electron emission properties of these NUNCD nanorods, which is much better than the NUNCD films, and also the beta enhancement factor, as I mentioned earlier, which represents the high aspect ratio. So it has a very high aspect ratio of around 1945. So, and also if you can see the lifetime, which can apply voltage of 250 volt, which gives a very high lifetime stability of more than 6,000 seconds. So NUNCD nanorods shows a very good field electron emission properties. So this is a one way of NUNCD nanorods. But we can also make a selective area deposition of NUNCD films, and then we can make NUNCD nanorods to further enhance the field electron emission. So the research is continuing. Like once you reach one perfect material, you need to think that what we can do further with this material and how we can enhance the material. So the questions need to be arises in our mind, so that we can think a lot, and then we can find the way how to get from NUNCD films we achieve NUNCD nanorods. The next step is that how we can grow a selective area deposition of NUNCD films. So step by step questions arises, and we can achieve one by one. So ask questions, multiple questions in our mind, try to get the answers, so we can do more research in the area, so that we can achieve a lot. So the next is the NUNCD nanorods, which has a pattern structures. So how we are following is that we follow the basic lithography process with plasma oxidation method. So first we use the nanodiamond seeding to grow the NUNCD films. So you can see this is the NUNCD films that we grown using this plasma lithography method as a selective area deposition. So you can see the selective area deposition, one NUNCD film, this is silicon substrate. So wherever this DGH, wherever the plasma oxidation happens, the diamond seeds in between here is etched out, and only the diamond films were formed on a circular pattern. And this is the, again we use nanodiamond mask. The nanodiamond particles will be sprayed on this on these DGH pads, and then we achieve DGH nanorods, that is the diamond graphite hybrid nanorod, because NUNCD films has diamond and graphite, as I mentioned in the TEM image. So you can see that vertically aligned nanostructures were selectively grown on these NUNCD pads. So how the electron emission achieved compared to the DGH pads and DGH films, this NUNCD nanorods shows a very low turn-on field and very good field enhancement factor. So the field enhancement factor increases, which increases the high emission current, as well as the low turn-on field, which represents from this low from this high aspect ratio. So to know the reason, again we carry out the TEM. So this is a another advanced version of TEM called the scanning transmission electron microscopy, in which we can find on a single NUNCD nanorods. So from here, we took only one nanorod. This is the only one nanorod, and the blue region shows the diamond, and the G region shows the graphite. So the presence of graphite in the nanorods again makes a very good electron conduction, so that it can achieve very low tenon field. So sp2 graphitic phases in the boundaries of the nano-sized diamond grains achieves a very good field electron emission with high aspect ratio. Now we have a selective area growth with one-dimensional nanorods. Whether we can go for flexible devices, because flexible devices are really more advantageous these days to go for very easiest and a compact nature of a device if you are fabricating. So how to make a flexible NUNCD pyramids? If you are, as you see, that diamond is the hardest known material, but diamond is very brittle. So we cannot achieve a flexible nature of diamond. So diamond is not flexible. So how we can achieve a flexible NUNCD? First is that we have made a pyramids in the silicon, is by etching the silicon material as an anisotropic etching using KOH. We can achieve a pyramidal kind of shapes in the silicon substrate. So these are the pyramids here. You can see the pyramids here. It's like a hole in the silicon, a pyramidal holes. And then we coated these silicon pyramids using NUNCD films. So these are the NUNCD films which is covered in these pyramids. And then we use a gold layer on these NUNCD films. After coating this gold, we use a polymer called polynorborine. So we made a spin coating of this polynorborine on this NUNCD films coated on these silicon pyramids. Then we reverse this by etching out the silicon. This polynorborine will become as a flexible nature, and NUNCD pyramids will place on this gold film that is between the diamond and the polynorborine. So we can achieve a flexible nature of NUNCD pyramids on this polynorborine. So these are the SEM images which shows very clearly the diamond pyramids are placed on this a polynorborine material with the interlayer of gold. This gold is useful for the electron conduction between each pyramids. So then we measured the field electron emission properties by using these flexible NUNCD pyramids in a bending way, and you can see that well, in a bending way for the flexible DGH pyramids, we achieved a low tenon field as well as a high field enhancement factor. So we also made a real-time device. So this is the field electron emission device with a lifetime of 700 minutes. Now, because as compared with the carbon nanotubes and graphene, that has only a 30 minutes, but the diamond materials having a very uniform emission without any decay in the current, in a bending nature, very uniform electron emission occurs with applied voltage or very less voltage with high lifetime stability. So the flexible NUNCD pyramids achieves a high lifetime stability with stable emission current even with the low applied voltage. So uniform and stable emission is achieved from flexible NUNCD pyramids. So again, in the beginning, I have told that carbon nanotubes and graphene achieves a low tenon field, but it cannot withstand for higher lifetime even with high voltage. But when you coated the NUNCD films on the carbon nanotube, this is the NUNCD film coated on the carbon nanotubes, and the Raman spectra shows the presence of diamond that coated on the carbon nanotubes, and you can see that the tenon field is really high as compared to the carbon nanotubes. But the lifetime stability is the important matter here. When you apply a low voltage to the carbon nanotubes, only carbon nanotubes, it can go only up to 30 minutes. But when you applying high voltages like 600 and 900 volt, which achieve a very good uniform electron emission and can withstand for longer lifetime, even more than 250 minutes with a very good field enhancement factor. So the NUNCD, which is coated on the carbon nanotubes, achieves a very good lifetime stability with very good field electron emission display. So now I'm coming to this microplasma illumination. Since we have achieved a very good NUNCD films that can be also coated on the carbon nanotubes. So how to utilize this field electron emission hybrid diamond materials for the next generation field electron emission devices. So the another generation is the microplasma illumination device, which follows the basic electron emission mechanism. So this microplasma is generated by electrical breakdown in gases by applying voltage. So the dimensions of the microplasma will be 10 to 1000 micrometer, so that we are calling as a microplasma device. So these are the some of the microplasma devices already reported in net by the other researchers. And why we need this microplasma? The application mostly people are using in the plasma displays and also in the plasma medicine. So this is the plasma torch which can heal your pains. So it's like a healing technique that plasma can be used. And other applications are ozone generation, environmental sensors, fuel cells, and material processing and cosmetics. So how the microplasma illumination device looks like? So this is the microplasma illumination device, as like the field electron emission, which contains an anode and a cathode. Here also an anode and a cathode. The anode is a ITO coated glass and the substrate is our diamond, which is separated by a spacer. And this complete device, which is placed in a vacuum in a vacuum system, and once at a particular pressure we pass the argon gas. So once apply the voltage, the primary electrons from the substrate will get emitted, and that will react with the argon gas, that will emit the secondary electrons. So the argon ions which make the plasma over here, that can be viewed from the ITO coated glass, because ITO coated glass is transparent, and then the secondary electrons which were collected. So to be as a requirement of a cathode for a microplasma device, it should have a large secondary electron emission coefficient. So it should emit more electrons, as well as the secondary electron coefficient should be high, and it should sustainability with micro discharge, low breakdown voltage like the low threshold like a low turn-on field, and stable high emission current. Why diamond can be used for this microplasma? Diamond has a very good secondary electron emission coefficient. Already we have shown superior field electron emission characteristics as compared to the CNTs and graphene, and low sputtering yield, because it's the hardest known material, so it has a very good rigidity and high thermal conductivity and high chemical inertness. So this is the microplasma device we fabricated with NCD coated CNTs, and this is the plasma photographs that we achieved from these NUNCD coated CNTs. And you can see that the first one for the CNTs, and which can turn on with even with low voltage, but it cannot withstand for a higher. So at 0 seconds you can see the brightness, and the brightness of the plasma is really uniform with 0 seconds to 21,500 seconds. But for the bare CNTs, the plasma is getting decay, so intensity of the plasma is getting decreased, and the lifetime is only going for 12,000 seconds. But the plasma is very stable till up to more than 20,000 seconds for the NUNCD coated on the CNTs. So better lifetime stability can be achieved using these NUNCDs coated on the CNTs in a microplasma device. We also try to coat the NUNCD on the graphene nanoflax. So this is the NUNCD coated on the graphene nanoflax, and this is the TEM shows the diamond is coated on this graphene nanoflax, and the colored HR, the high resolution image, shows that the green region shows the graphene and the yellow region shows the nano diamond particles, which is coated on this graphene nanoflax. That represents a very good high stable electron emission of high voltage with high intensity of 540 volt as compared to the only with the graphene nanoflax. And you can see that the stability is really good of more than 1500 seconds as compared to the bare graphene nanoflax. And you can see that the graphene nanoflax were completely etched out around 500 seconds. But if you see the nanocrystalline diamond coated on the graphene nanoflax, which can go for more than 1500 seconds, and the NCD coated on the graphene nanoflax is not etched out by this plasma. So this is very stable with a good electron emission as compared to the graphene nanoflax. Again, the nanographitic phases in the grain boundaries achieves a very good electron transport mechanism, with a good improvement in the plasma illumination characteristics. If you want more information about this work, I would suggest to go through my review article published in 2014. Is based on the flexible NUNCD films and also the novel aspects of diamond. Is a book chapter published last year. So both these articles will represent the how the nitrogen incorporated UNCD films or the nanocrystalline diamond films helps for the field electron emission applications as well as in the microplasma applications. So now I would like to focus on the field electron emission properties of the UNCD films using the gold ion implantation. Why we need implantation? Because implantation can be achieved in a low temperature. Even in a room temperature we can achieve it, but the nitrogen grown UNCD films that we need high temperature. And we can also dope various species inside the materials so that we can do implantation very easily to get highly conducting UNCD. So this is the basics of the ion implantation. The ions of a material are accelerated in an electric field and impacted into a solid. So this process is changing the physical, chemical or electrical properties of the material. So once implantation, we anneal the material to heal the damages and also to make the dopants that place inside the material to be more active. So this is the ion implanter in Indira Gandhi Center for Atomic Research, Kalpakkam. We had a collaboration with Dr. B. Sundravel there, and we made gold ion implantation UNCD. So this is the UNCD films grown on silicon. This is not nitrogen UNCD. These UNCD films were grown in methane and argon plasma. Then we use a gold ion beam of a 500 kilo electron volt with dosage of 10 power 17, and these gold ions are implanted on the UNCD. There forms the UNCD with gold. So this is the gold UNCD implanted with the gold ions, and you can see from the SEM MEDAX that presence of the gold. But for the us grown UNCD, there is only presence of silicon because we grow the UNCD on silicon substrates. And how the gold ions presence in the UNCD. This is the TEM image, that is some HADIF image. We need to acquire this gold ion implanted UNCD. These gold nanoparticles presents in a way of a spherical shape in the UNCD films. So the presence of the gold nanoparticles inside these UNCD films, the conductivity of the material is improved, and also by increasing the gold ion dosage, the turn-on field is greatly decreased, and also the current density is really increased if it increases the gold dosage. So this is the gold ion implanted UNCD, which is grown on silicon substrate. You can see that we achieved, but the gold ion implantation the enhances the field electron emission properties that grown on the silicon. But the UNCD and silicon, the interface, you can see here there is presence of amorphous carbon. Even in the grain boundaries, we saw amorphous carbon when the films were grown in methane and argon plasma. So we removed that amorphous carbon from the grain boundaries by incorporation of nitrogen, also by gold ion implantation. But the interface should also to be considered to transport of electrons from silicon to the UNCD. How we can do that? So we have used a gold interlayer from UNCD to silicon, and then we implanted with gold. So gold interlayer with gold ion implantation, and we achieved a low turn-on field of 2.6 with high current density. To know the reason why, how this gold react with UNCD and silicon as a interface, and how the gold ion implantation which makes efficient field electron emission, we carry out the TEM, as well as also the lifetime stability is also compared with these other well-known field emitters, and we found that this hybrid diamond with gold material shows a very good lifetime stability, more than 1000 minutes, as compared to the other field emitting materials. So to know the reason, we carry out the TEM. So this is the bright field TEM, which shows this is the gold implanted region, and this is the gold interlayer region. If you see in the gold implanted region, the presence of gold here. This is the gold particles, and this is the diamond particles, also with some graphitic natures in the interface between the gold and the diamond. So gold acts as a catalyst to induces the nanographitic phases in the diamond. Also, you can see here, this is the interface region, and there presence of some silicon carbide between the UNCD and the gold. So silicon is interdiffused inside the gold and forms some silicon carbide clusters in a nanoparticle sizes that will enhances the electron transport between the silicon to the UNCD, which achieves a low tenon field. Also, we carry out further studies with TEM, EDAX, as well as some HADIF images, and which confirm the presence of carbon. So silicon forms as a silicon carbide between the gold and the UNCD films, and the colored images from the TEM also represent the presence of silicon carbide gold in the interface between the gold and the UNCD. So the formation of the gold silicon eclectic layers that forms the silicon carbide clusters in the interface that helps for the electron transport, and the nanographic phases in the interface that also makes a very good transport mechanism which helps better field electron emission properties. We also use this gold and implanted UNCD on gold coated silicon for microplasma devices, and we achieved the hybrid material with diamond and gold shows a very good intensity plasma even with low applied voltage as compared with the other other field emitting materials, and the lifetime stability is also very good as compared with these other field emission materials. And if you like to know about more about this diamond gold nano hybrids for the enhanced cathode material for field electron emitter applications, I would suggest to go through my review article in 2021 recently published along with my supervisors in Belgium and in Taiwan. So as a summary, we have achieved NUNCD films with enhanced field electron emission properties, and then we fabricated the NUNCD nanorods with high field enhancement factor. And these NUNCD films can be coated on CNTs and graphene nanoflags to achieve a high stability microplasma illumination properties. We have also successfully fabricated the UNCD gold nanohybrids, and these gold nanoparticles induces nanographic phases, which leads to the enhanced field electron emission properties. So the final thing is that the betterment of the field emission as well as the property as well as the microplasma illumination and electrical conductivity is attributed to the incorporation of sp2 graphitic phases within the grain boundaries of diamond films that forms a very good electron transport that within the material and also in the vacuum if you go for the one-dimensional materials. So the nanographic phases in the grain boundaries are the main key factors for the enhancement of the field electron emission properties. So finally, I would like to acknowledge my my professor from Hasselt University, Belgium, and my professors Yinan Lin and my professor Tai Nian Hua from Taiwan, and my collaborators and my colleagues from IGCAR Canada and from Taiwan for carrying out these interesting works with the diamond. So these are the facilities and ongoing research work that I'm carrying out in CSIR IMMT from last 1 year. So we have a system to grow the diamond-like carbon, also the diamond films here, and with a microwave plasma CVD. And this is the RF and DC sputtering system. Can we grow the metal oxide thin films? And recently we carry out the work with dielectric barrier discharge, where we can do some oxygen, we can do some plasma treatment on any kind of material to change to hydrophobic to hydrophilic nature. So we are working on this dielectric barrier discharge system, and we have an electrochemical workstation to use this conducting diamond for some sensors as well as in supercapacitor applications, and Hall effect measurement system in our lab to know the electrical conducting behavior as well as the Hall mobility, Hall electrical carrier concentration. And this is the recent system to achieve a laser induced graphene on a polymer substrate. So this is the graphene that can be achieved on the polyimide substrate that we can use for some flexible devices, and this is the plasma illumination devices which is fabricated recently from my PhD student, and the gas sensing system with my colleague. There we can sense many gases, especially with hazardous gases can be detected to know to fabricate a sensing device, gas sensing device. So I would like to invite you people to come over here for collaborative work as well as for dissertation work in our group for a better learning of plasma based devices for various applications. So this is my email ID with my contact number. So finally, I would like to thank you all for your kind attention. So now I can expect questions from the audience. Thank you so much.
Thank you, sir.
Yes, ma'am.
Any questions from the audience? Sir, we are having your email ID and phone number with us.
Yes, madam.
Some questions about materials are there in the chat in the beginning itself. I answered directly.
Okay, ma'am.
What's material, and I will forward you the questions that we'll get through the YouTube and all.
Yes, ma'am.
So thank you very much for your eminent presentation, starting from preparation of artificial diamond to the present ongoing enlightening works. Sir, thank you very much, and also thank you for inviting our budding engineers and the scientists to collaborate with you, and the work, if they wish, they can do there. And thank you very much for your eminent talk and
Yes,
for
ma'am.
your
Thank you.
time for us. Thank you very much, sir. We will meet
Yes,
you
ma'am.
through your phone call. Thank you,
Yes,
sir.
ma'am. Yes, ma'am.
Thank you very much, sir.
Yes, ma'am. Thank you so much, ma'am.
Yeah, welcome, sir. Vidya,
Yes, ma'am.
madam.
Thank you, sir, and thank you, ma'am. Now I request Dr. D. Appalraju from the Department of Science and Humanities to introduce our second speaker, Dr. T. Pavan Kumar.
Thank you, madam. Thank you, madam. Good afternoon, all. This is Dr. Appalraju, Faculty of Management for Engineering, Department of Science and Humanities. It is my great privilege to introduce a brief profile of eminent scientist Dr. T. Pavan Kumar. Sir completed his graduate and postgraduate BSc and MSc from Osmania University, Hyderabad in the year 2002 and 2004 respectively. Organic chemistry with drug design specialization. He did his PhD CSIR IACT in the area of research in synthetic organic chemistry from Osmania University, Hyderabad in the year 2011, and completed PG diploma course Patent Law, Nalsar, Hyderabad in the year 2012. He also completed his postdoctoral at NDSU, Virgo, USA in the year 2015. Dr. T. Pavan Kumar starts his career in teaching in Loyola Academy, Hyderabad, and research in Reddy's Lab, Hyderabad in the year 2004, and worked many prestigious institutions and research organizations like CSIR, IACT, Doutlera, Hyderabad, NDSU, USA, NRDC, New Delhi, IASC, Bangalore, and presently is working as a senior scientist, CSIR, IMMT, Bhubaneswar, visiting faculty, ICT, IOC, Bhubaneswar, and IISCR, Berhampur, Odisha. He published more than 21 research publications in the national and international reputed journals. He got patented more than 22 titles in his area of research. It includes more than 5 US patents. Dr. Kumar conducted, presented, and participated more than 73 conferences, workshops, symposiums, and seminars. He bagged a number of awards and medals in his career. University first and won 4 gold medals in MSc in the year 2004. DST Inspire faculty in the year 2012. Assistant Professor AC SIR 2014, Telangana Young Scientist Award in 2015, Serb Young Scientist in 2015, WIPO IP Patent Scholarships in 2016. Sir has also life member of in different reputed professional bodies like Andhra Pradesh Academy of Sciences, APAS, Chemical Research Society of India, CRSI, Department of Science and Technology, DST, Science and Engineering Research Board, SERB, Material Research Society of India, MRSI, Indian Society of Chemists and Biologists, ISCB, Indian Science Congress, ISC, Global Intellectual Property Convention, GIPC, and Institute for Engineering Research and Publications, IFERP. This is a brief resume of Dr. T. Pavan Kumar. Even though Sir has more achievements in his career, I mentioned here very few and brief due to time constraint. Thank you, sir. Having you our resource person in this session. Session hand over to Dr. Praveen Kumar, sir. Thank you.
Thank you, Dr. Appal Raju Garu. I will, because we are Telugu people, I add some Telugu terms. If non-Telugu people are there, please bear with us for some time so that you will be learning new language or new kind of conversations. And thank you for your nice introduction. And first of all, I thank all the organizers for inviting me to this webinar. And I also specially thank your Vice Chancellor, Sir, Professor Jagannath Rao Garu, and Principal Madam, Dr. Persis Garu, and Kirti Madam. You are anyway here. We were in good contact for the last few months, where she was putting a lot of efforts in designing this program. I really appreciate your efforts, Madam. And also, here I would like to mention Dr. Jagan Mohan Reddy. He was one of my best friend and colleague. We happened to attend several programs here and there as part of chemistry refresher courses or other programs. In that manner, he has introduced me to your university. And I also find that Principal Madam or VC's Vice Chancellor, sir, they were citing my association with your university. So good to know this. And further, I would like to add that Vice Chancellor sir has emphasized the importance of intellectual property and innovation. And what I felt is he has a very good understanding about these concepts. And being in that administrative role, and he could able to give us some points which were of very, very recent relevance. When we compare IP contributions from China as well as comparison with India or any other matters. So I was really surprised to notice this, and I felt very happy, because having such kind of leadership for an organization is very, very important. And it itself shows that your organization is of with full motivation. And I feel after attending these sessions, at least some of the young and bright students will come forward to nurture their ideas into fruitful outcomes. So with this briefing, I just share my screen. Today I'll be talking to you on the aspects of intellectual property rights. Please let me know, is the screen visible?
Yes, sir.
Yes.
And I have made it in slide mode only. I think it is in slide mode. Yes?
Yes, sir.
Yes,
Okay.
yes.
Okay. So the concept that we discuss here are on IPRs. So that is the reason why I put the title as Overview on Intellectual Property Rights, Importance and Relevance to Material Science and Engineering. Because I find that the students or the faculties or other attendants present here are mostly from a material science and engineering background. So therefore, I thought I'll show some examples or case studies which are relevant to material science aspects. And most of my slides will be pictorial in nature, and I try to depict most of the material so that you can easily grasp it, because I feel it's a very new concept. Just to begin with, look at this slide, and please let me know whether you find any problem in this query, in this cartoon. All I asked was, can I patent my copyrighted trademark? Just look into this query, and please, you answer yourself whether do you find any problem with this query or not. And if you don't find any problem, once again I am repeating, if you don't find any problem with this query, then certainly you all need to put 100% attention to these slides or this lecture. Please don't turn your eyes, otherwise you may miss something. So therefore, if you are not finding any problem, then please be 100% concentrated. If you feel that, yes, sir, there is some problem, then certainly you might be having some or other kind of direct or indirect awareness. And let us clear all these aspects in coming slides. So therefore, this is the presentation layout. We'll be quickly looking into the introduction and importance of IPRs. And we'll also see some types of IPRs and their examples. Then we'll talk about what is called creativity and what is its impact over science or research or development, whatever we call so. Then we look into some examples, and I'll give a special mentioning on nanotechnology case study. I'll show you how the countries are performing in this area. And finally, we'll end up with some takeaway messages. And this is my background. I think anyway, it has been covered. And these are my contributions. And here I must tell you that I have a parallel expertise of research as well as intellectual property. Until I completed my PhD, I was not aware of any topic or any concepts of IPR. I did not even look at a patent. But unknowingly, I got an opportunity to work with an IP company. There I realized the importance of IPR for researchers and academics. Then I realized that I should parallelly explore this activity. Then only we can convert some of our research works into useful outcomes. So that that idea, or you can say like what that thought, has helped me to build a parallel career or parallel expertise, so that most of our research works could be translated into patentable outcomes. This slide is a reflection of all these efforts. Then, when we talk about IPR, see, we come across so many terminologies. IPR deals with industry, protection, trademark, brand, patent, invention, copyright, infringement, licensing, secrets, law, this, that. Everyone is talking about these things. Whether irrespective of their academic background, irrespective of their professional background, nowadays IPR has become a subject of major concern. Why is it so? Look at this slide. When you look at this, the answer is right away there. Yes, it is a matter of concern, because we always claim that India has got all the potential by way of knowledge, by way of intellect, by way of working efficiency and everything. If that is so, if we are so intelligent, why is that our ranking is like this? Then that means we have not realized to the extent that we have to realize. So therefore, now let us look into the basic concepts of IPR, then come back to the statistics, and then connect these discussions to the final outcomes. So in this fashion, we'll make our discussions. When we talk about intellectual property, there is an organization called as WIPO, World Intellectual Property Organization, which is a global agency which looks after IP matters of different countries, and all countries are member states of this organization. And it monitors or manages these activities, so that a transparency in these activities will come into place at a global level. According to them, the definition is like this: intellectual property refers to creations of the mind, inventions, literary and artistic works, symbols, names, images, and designs that are used in commerce. Please read this definition properly. It is, intellectual property is nothing but the property which is a creation of our own mind. Then, when we talk about property, or when we feel that we have a property, we also feel we have some right. Yes, it is my property, it is my right. So similarly, when you compare intellectual property with other kinds of property, yes, it is like this. Like any other property, intellectual property can be used, can be sold, can be licensed, can be mortgaged, can be gifted to anyone, whomever you wish. But the major difference between these two properties is, unlike the traditional property, intellectual property cannot be enjoyed for longer time. It is for a definite period of time. That is the reason why we are talking about the concepts of IPR, how to do, where to do, when to do, and how to proceed. All these things are coming into place. And IP as a property has these many advantages. It gives economic rights to the creators. And if you have an IP, you can use it for commercial exploitation. You can use it for generating some capital expenditure. You can use it for technology transfer. And overall, it can be used for cultural development of a society or of an organization or of a state or of a country or of a close proximity, whatever it is, or communities. And when we talk about other countries, wherein we cite the examples of US or Japan or some other Western countries, which we call them as developed nations, they are developed because they have a cultural development as well, for which IP has played a very, very important role. So therefore, as I told you, I repeat again, IP as a property can be sold, can be bought, can be leased or rented, can pass under a will, and it can be assigned to someone else, whomever you wish to do so. And to summarize, creation of human mind and its output is called as intellectual property. And the rights are given by statutes of the nation, and these are called as exclusive rights. Always these IPRs or intellectual property rights are attended with some limitations and exceptions. And they are time bound and territorial bound. These two are very, very important, time bound and territorial bound. And here is the slide which describes the types of IPRs, different types of IPRs. Broadly speaking, intellectual property can be divided into two major categories. One is copyright, the other one is industrial property. Under copyrights, you can see the rights of authors and rights of performers. And under industrial property, again, it has two subdivisions. One is based on information, the other one is based on innovation. When I talk about information, the trademarks and geographical indications comes under this. Under innovation, the patents, trade secrets, and industrial designs will come under this category. So here is the broad classification. Now on the left-hand side, I tried to show you all these different types of IPRs with an example each. If it is a trade secret, the formula of Coca-Cola is a trade secret. Copyright, there are many copyrights. For example, Harry Potter, written by J.K. Rowling, it's a copyrighted novel. And patent, any technical features of a mobile phone or any other equipment or any process or any product, you can get a patent. A design, the mobile phone that you are using has different designs depending upon the company or depending upon the model that you use. That itself is a design. And Darjeeling tea is an example of geographical indication. Now, after knowing what is called IP and what is called IPR, then how did these IPRs evolve? Yes or no? There is a concept called as evolution. Like we talk about human evolution or evolution of different subjects or different fields. Similarly, IP has also evolved over a period of time. And if we connect it back for our sake of understanding, then it is like this. We are talking about a property. When we have a property, we get some rights. And if this property is from our intellectual creation or from our mind activity, then it is called as intellectual property. And the rights are called as intellectual property rights. But where do we start for all these things? It is very, very important. And it all starts with an idea. So ideas are very, very important. If I ask you how many ideas do you generate per day, the number may go in thousands. But are your ideas really useful ideas? Then the answer might be difficult. So therefore, all IPRs have an origin which is an idea. So they'll originate from ideas that we generate. If you have an idea, if it leads to expression, then you will get a copyright. If you have an idea, if it leads to invention and innovation, then you will get a patent. And idea, if it leads to quality and identity, then it will be a trademark. And idea leading to appearance in the sense only appearance, then it will be a design. And idea, if you can keep it confidential in the sense confidential, you should zip your mouth. If it is possible for you to make this, then that can be treated as a trade secret. And here I try to show you all these IPRs with an example each again, so that you can easily understand the concepts. Now, why is it that the study on IPR or the knowledge on IPR is so important for academic and research people? We feel that it is not our business. Why should we worry? No, that is a wrong attitude. It is very much important to all of us, whether it is me, you, or whoever it may be. It is because the reason is right away here. Whatever products or whatever technologies we see in the market, there are a lot of efforts going behind to bring them into the market. All those efforts, we feel that is research and development or research and technological development. But however, if you properly analyze, there is a lot of gap in these activities, and this IP can definitely help in filling these gaps so that proper research and development activities can be brought up into useful products. That is where we can realize by the end of today's session how IP plays a very, very important role in converting most of our research works into useful outcomes or productive outcomes. Here I try to show you the same concept with an example. If you have an idea, see, I think about 20-25 years back, there was no mobile phone. Until I did my MSc, I was not aware of mobile phone. But now, a small kid, 1 year or even less, they are aware of mobile phone, and they can use mobile phone very much better than us. It is because there is a technological growth. And if you take the example of mobile phone, someone has got an idea to develop this. Therefore, it is not that directly today he got an idea, tomorrow he brought the mobile phone in the market. It is not like that. It took several years or maybe several decades for them to convert their ideas into workable ideas, to bring them into a product form, and then bring it to the market. So this is how a technology-led idea going to the market. These are all the sequences. If you have an idea, then you have to work on that one to make a proof of concept, then try to make a prototype, then try to make scale up, then try to take it for commercial production. Finally, you can bring that product into the market for public use. For doing all these things, you need a lot of money, lot of energy, lot of time, everything is required. But only those who can successfully perform all these activities can see the marketplace. Otherwise, they will not show up their technologies. So that is how, if 1,000 efforts have gone, if 1,000 people are working for mobile phone, maybe hardly 5 or 10 people or 5 or 10 works may see the market phase, not all the 1,000. So therefore, knowing about IPR and applying the concepts of IPR in our day-to-day research activities are very, very important. And from here, we'll try to look into different types of IPRs, starting with the trademark. Please read the description present here. Trademark is a name of an enterprise or a mark capable of being represented graphically, distinguishing the goods or services of one person from those of others. That means you should be capable of distinguishing yourself from others. For example, your university is there. Just look at your ID cards. There'll be a logo, emblem will be there, university logo. That itself is a identity for your university. So likewise, it can become a trademark. Similarly, for any business which are product based or service based, they have to show up their identity. So therefore, look at this. Coca-Cola, Yahoo is a service mark. So marks on goods, service marks, certification trademarks, collective marks, well-known marks, trade names, all these are the examples of trademarks. Even look at this. A trademark can be a word mark, device mark, signs, symbols, logos. I think now you might have got a good awareness what is called a trademark. Now, whenever you visit a market, whenever you visit some other places, you try to find out what is the trademark. There is a Benz car and there is a Maruti Suzuki. If I give you an option to visit our institute, which car do you opt? You have two options. One is Mercedes Benz, the other one is Maruti Suzuki. Which one do you opt? Certainly you may go with Mercedes Benz. You feel that, oh, that is very great. Yes, because its brand image is more. So that is where the trademark is. So these are all some of the examples of different trademarks. Now let us look into the copyright. Copyrights are again very, very essential. But however, in India, we are not implementing to the extent that we have to do. Copyright is a legal term describing rights given to creators for their literary and artistic works. All the time I am taking the example of Harry Potter. You may get one doubt. Why is it so? There could be many people. Yes, even Jawaharlal Nehru had got a copyright. Even Indira Gandhi has got copyright. Rabindranath Tagore has got copyright for his Gitanjali. Yes, all these are famous. But this specific example I am taking because J.K. Rowling, the author of Harry Potter, is considered to be more richer than Queen Elizabeth. That is the reason why I am taking always this example. So she is considered to be more richer than Queen Elizabeth. Oh, how is it that? Yes, that is the power of intellectual property. And Queen Elizabeth is richer by inheritance. But J.K. Rowling is not by inheritance. It is by her intellectual contribution. So that is where intellectual property plays a major role. And this example itself is sufficient to make you realize the impact of intellectual property. So therefore, under copyrights, literary works or textual materials, audio materials, dramatic works, artistic works, architecture, advertisement, maps, technical drawings, computer programs, databases, all these things will come under copyrights. Here I will show you some of the examples. Look at this. All these are the examples of copyrights. Painting, cartoon, advertisement, or paper poster, anything. Even these are the examples of copyrights. Cinematography works, musics, textual materials, even your dissertation work or thesis work, all those have to be copyrighted. But of course, to what extent we are practicing that only we have to realize by ourselves. So that is about copyright. Now I'll introduce geographical indications to you. And this again, geographical indications has a lot of significance with Indian context. Why? Because we have unity in diversity by many means. And one means is by climatic conditions or geographical locations. So therefore, a name or sign used on goods originating from specific geographical origin or location and possessing qualities, reputation, or characteristics that are essentially attributable to that place of origin. So geographical indication is so simple. The place from which it originates, it has the reputation and characteristics belonging to the geographical conditions of that particular place. Darjeeling tea, even Mysore silk, Mahabaleshwar strawberry, Nagpur oranges, Agra peta. Likewise, if I start telling, the number may not end. Even now, by now, you might be getting some ideas. You might be knowing some of the examples of geographical indications from your own place. Mangalagiri saris, Kanchipattu saris, or Venkatagiri saris, all these are the examples of geographical indications. I'll show some of them here. Alipi coir, Naga mircha, Scotch whiskey from Scotland, Pisco from Peru, Nashik grapes, Kashmiri Sazani craft, and what are all can be geographical indications. A geographical indication can be any agricultural product or a foodstuff, wine or spirit drink, handicraft, clothing, industrial product, anything. So any of these things can be geographical indications. Even the jasmine flowers, they are also classified into geographical indications when they have registered. For example, there is a flower called as Mysore Malligi. Another one, Madurai Malligi. Both are Malligi. Malligi means jasmine, but both are jasmine only. But one is from Madurai, the other one is from Mysore. Similarly, there is one more jasmine from Madurai, which is called as Madurai Saugandhi. So all these are the examples of geographical indications. Now, even you can search if you wish to know that different geographical indications from your place or from your state, you can just go into Google and search them. You can find out. So then you realize, oh, all these examples are geographical indications. We were very much using them, but we were not knowing that they are geographical indications. So that means IP is there in each and every part of our activity. Now, let us look into the industrial designs. As I told you, if you have an idea, if it leads to appearance, then you will get an industrial design. But here, it will not cover the technical features of the article to which the design is applied. So therefore, ornamental or aesthetic aspect of an article is protected, such as three-dimensional or two-dimensional features, shapes, colors, patterns, lines, etc. And these designs are applied to products of industry and handicraft, technical and medical instruments, watches, jewelry, housewares, electrical appliances, luxury items, vehicles, architectural structures, textile designs, etc. On the right hand side, I am showing you some of the pictures. Forget about the pictures here. Even if you look at your own yourself, maybe now you might be using some paper or pen. Those pen, maybe a Reynolds pen or other pen. So that is a design. And some of you might be having spectacles of different design. There are different designs. And if you are working in a chemistry or biology lab, you might be using different syringes. So each company has syringes of different design. Those are different designs again. The bathing soap, Lifebuoy, Lux, or others, Peers. So they have different designs. All they are protected under designs. Even especially for the ladies or women, you might be wearing a lot of jewelry. All those jewelries are protected under industrial designs. That is the reason why the designs that you get in Lalita Jewelers will be different, and that you get from Khajana or Malabar Gold or Kalyan Jewelers. There are different jewelry shops. So those designs are unique to that particular shop, not the others. It is because they have IP protection for those designs. See, these are the examples of industrial designs. All these, even toothbrush, Colgate, Oral-B, Palmolive, it's like based on the company, you get different design. Based on the model, you get different design. So all these are the examples of industrial designs. Now let us look into the trade secret. As I told you, if you can keep it secret, that means you have to zip your mouth. In whatever case it may be, you should not disclose it. If you can maintain that, then you can go for a trade secret. Here are 4 famous examples for the trade secrets. The first one is the composition or formula of Coca-Cola. Even as on today, no one knows the exact formula of Coca-Cola. Now you may feel, sir, I am a chemistry person, or I am a pharmacy person, or I am a biologist. I can easily do reverse engineering and make out what the composition is. Yes, many people tried, but no one could succeed. So that is how trade secrets have to be maintained. The other example is original recipe of KFC. You all might be going to KFC. You might be very much fond of eating in KFC, but the original recipe of KFC is a trade secret. That is how they could able to maintain that. That is how they could able to capture the market. And spray lubricant, which was invented in the year 1953, it's a trade secret. And the Google page rank algorithm, whatever you search in Google, some results will appear. How do you get those results? That's again a trade secret. Now, let us look into the patents. Patents are again very, very important, especially for the research community. Why? Because most of our research works can be easily translated into patents or patentable outcomes. Trademarks, copyrights, geographical indications, trade secrets, industrial designs, they're also equally important. But however, in practice, patents are very much relevant to our day-to-day research works. And that is the reason why even in today's session, we will give more emphasis on patents. And in simple terms, a patent is nothing but a contract between the government and the inventor. In very simple terms, it's a contract between the government and the inventor. Inventor means the people like you and me who have worked on a research problem and come up with some solution. Government means or the patent office. We file a patent to them so that they will give some rights to us. It is like a contract between the inventor and the government. What happens here? Whenever we file a patent, the government gives the inventor the right to exclude in the sense stop, the right to stop others from making, using or selling the invention for a particular term of years, generally 20 years in case of patents. So therefore, if you have a patent means we can stop others from working or using of our invention. That is the simple and easiest definition for a patent. And therefore, in a single word, we can call patent as a techno-legal document. Techno-legal document. Techno means a technical part of the document. It is almost all similar to the manuscript that we make for a publication. But the legal part is more essential. That is where you get the rights. That is where you get the protection. It is like the boundary of your property. So that is the legal part. So therefore, writing a publication might looks to be so easy. Once you start practicing, you can very well write it. But however, writing a patent is not an easy task. And that is where one has to learn these skills so that while you perform some research activity, you will also know how to convert those into patentable activities. After discussing different types of IPRs, let us look into this slide, which explains different types of IPs in one example. Mobile phone is there. The logo or the name is a trademark. It is protected as a trademark. The shape of this mobile phone is protected by industrial design. Improvements or any technical features, they are protected by patents. The software is protected by copyrights. Even the user manual is also protected by copyrights. So this is how a single product or a single object may have different types of IPR. It is not that mobile phone should only have patent or it should only have trademark. No, it can have several IPRs within itself. Similarly, look at this example again. Washing machine, Bosch company has bought this, but design is a, body is a design, user manual is a copyright, engine and drum are patents, and Bosch company has made several designs of these washing machines starting from 1907 to 2001 with a different brand name they have brought. So all they come under trademarks. So this is how one can capture the market with the help of IP. And this is the duration of protection for different types of IPRs. For patents, generally 20 years, they cannot be renewable. Trademarks, anywhere between 6 to 10 years, the same with designs. But however, these two can be renewable. Copyrights, the protection is valid till the 60 years after the death of the creator. So I think Rabindranath's copyright on Gitanjali has got expired very recently, maybe in 2010 or 11. So that is the impact, or that is the kind of importance the IPR has got. And after knowing the very basics on IPR and also different types of IPRs with an example, now let us look into the creativity, concept of creativity, because we feel that whatever we contribute towards IP or towards technology, it all starts with an idea. If you have to have an idea means you have to be creative, because normal ideas everyone will get, but we don't need normal ideas. Sorry. We don't need normal ideas. We need some ideas which are so creative so that they can be translated into useful outcomes or IPR outcomes. So therefore, creativity is the ability to come up with new idea or design new inventions or work in new ways or solving problems in new ways, so that we can try to generate workable ideas and own them in the form of IPRs. One has to think away from the box. That is what is required. So when we talk about this, certainly the next question that arises is it that you are great, or I am great, or someone else is great? Who is great? Because everyone has the capability to generate ideas, and everyone is creative. I am creative in my own ways, you are creative in your own ways. But is there any way to judge who has greatest level of creativity? Suppose if there are 5 people, if I like any one of them, I feel that, oh, he is more creative, or she is more creative, but it may not be true. So then this question is like a never ending question. I think finding a proper answer for this kind of query is very, very difficult. But we all can compromise, provided if I say that the one who has created the human being has the greatest level of creativity, then certainly we all agree, yes sir, yes sir, yes sir, yes or no? Yes. So whether we call God or superpower, whatever it may be, that has the ultimate or the greatest level of creativity. But however, now look at this. Who are creative here? You, me, who is this? We don't know. But when we take the shape as a human being, then certainly we got the ability to think and create. That is where the superpower or supernature or the God, irrespective of the religion, we all believe in God. Those who do not believe in God, we all believe in nature or superpower. That itself is the same, which is beyond us. But we don't know. We did not see them properly. So therefore, we have been created, humans have been created with a mind. The only difference between a human being and other animals are, it is the mind. We have mind, they don't have proper mind. That is what we feel. So therefore, this has made us to think in a creative dimension. That is where scientists could able to find out pH values of different organs from the human body. See this. We all might be conducting experiments in the laboratory to find out the pH of a chemical process or some product or some biological process here and there. But scientists could go very much far to find out the pH values of human body. If I ask what is the pH of our brain, it is about 7.1. Our saliva about 6 to 7.4. The pH of heart is about 7 to 7.4. So all these things. Then the bone, our bones also have some pH. There's about 7.4. So this is how. So that means human beings are very much creative. Like you and me are so creative. As such, a human body itself can be termed as a chemical factory. Chemical factory or also a biochemical factory. But now, at majority of the times, we get confusion between what is called discovery and what is called invention. Sometimes we feel both are same. Sometimes we feel both are different. If someone asks you, what is the exact definition of an invention or a discovery? Then we say, we know, but we try to give big explanations. But that is not correct. To be inventive or to contribute to IP, one has to have the knowledge of discriminating between the discovery and invention. If you can able to identify what is an invention and what is a discovery, then only you can effectively contribute to IP. Otherwise, no, you cannot contribute because you yourself will be in confusion or in dilemma. So therefore, discovery is something which is already known in the nature, but you are the first person to show it to the world. Whereas invention comes with problem solution approach. There is a great saying, necessity is the mother of all inventions. So therefore, whenever there is a problem, that means we feel that there is some problem. We have to find out some solutions. Then we start thinking, oh, I have to do this, I have to do that, or we can work in this manner, that manner, so that we can solve this problem. So that is what the invention is. So therefore, always invention stands at higher stage than the discovery. Look at this. Who is he? By now, I think you all could realize the name of this person. If no, he is Archimedes, and he has discovered the theory of buoyancy. See, He is so shameless. While he was taking bath in bathtub, he ran away like that, without thinking whether he is going in the streets or people are looking at him or not, because the creativity or the craziness has gone to that level. All the time he was occupied with thoughts, generating ideas, adding creativity to that one, observing the nature, so that he could come up with theory of buoyancy. Even if not Archimedes, even if I or you, some of you or any of us, we are in that position, same thing would have happened. But we are not so shameless, but we are not so creative also. We are very happy. Oh, I got bathtub, I am taking bath. If it is half an hour, more good. If it is 1 hour, even more good. I will enjoy. If it is for free, even more good. That's all. But this person has brought the theory of buoyancy, which was already there, but he has shown it to the world. Look at these people. Because there are many engineering graduates, I think, when I ask my engineer to build a single bedroom with attached bathroom, this is the outcome of one of the creative engineer. Attached bath, single bedroom with attached bathroom. And look at these children. We have to appreciate them. They are from the remote village from Tamil Nadu. They don't have proper facilities. But how to do? Now, Swachh Bharat Abhiyan has come. So therefore, but no facilities, no money, then what to do? They were visiting one town. They found some plastic bottles on the roads here and there, falling on the roads here and there. Then they got this idea. And now, see all the exercise that they did to make their arrangements. I tried to show you here. So that is how idea, creativity, and connecting them to useful outcome is very, very essential. During COVID times, we have to sit at home. We cannot go out and we are workless. Sometimes we go into depression. Sometimes we don't feel good. Sometimes we feel bored. One of the creative person, maybe he might be having only kitchen utensils. Then he has brought up this. It is the level of creativity. Highest, one of the good level of creativity. So then now let us look into what is called invention and innovation. Something which is solved for the first time. That means the first solution. The first solution is called as invention, and any improvements over the existing so that our lives become more easy are called as innovations. For example, the very primitive wheel. The early human being has developed a very primitive wheel, maybe with wood or with stone. That was the invention. But now geared wheels are there, powered wheels are there, these many wheels are there. All those improvements are innovations. Similarly, internet is an invention, whereas the use of internet for developing social media is an innovation. Look at this in very simple terms. In olden days, people used to use these kind of cricket stumps, yes or no? But now all are sensor based. So once upon a time it was an invention, but now many improvements have taken place. This is the example of innovation. So here are some of the greatest examples of inventions that the humankind has witnessed and which have also helped us to lead a better life. Steam engine, gyroscopic compass, television, telephone, radio, automobile, aeroplane. All these are some of the examples of greatest inventions. Now, from here, let us look into the patents in an elaborate manner. When we talk about a patent, as I told you, it is a conditional grant. It has some limitations and exceptions. It has the balance of rights and obligations. It is also subject to other laws of the land, and it is always granted to the inventor or his assignee. We feel that patenting or IPR is a very new system or very new culture. No, the history dates back to 500 BC. Even during those times, granting of protection to inventors was in good practice. And this is the slide which shows on the timeline of history of patents. The word patent has come from the Latin word, literary patentis. We all know many of our modern terms, they have originated from Latin only, right? Similarly, the term patent also comes from Latin, literary patentis, which means an open letter. you are inventing something, you are filing a patent to the patent office or the government. That is, you are opening up on your invention. So that is the reason why the term has come. And this is how the first pages of patents look like. Here I try to show you two examples, one from United States, the other one is from PCT application. These are the examples of first pages of the patent applications from two different patent offices. If you look at these detailedly, you will find classification, some dates, some numbers, some names, and also titles, some references, all these things are there. That means the first page of a patent is called as a bibliographic information or bibliographic data, which gives you lot of insights on the status and also the people involved and this invention timeline, so that you can easily make out whether your work is already there or not, or if you wish to perform a search, or if you wish to go through a patent document, it can provide you the details on all these factors. That is called as bibliographic information or bibliographic data. And if you have a research work, now if you wish to go for a patent filing, then you have to establish that your research work will get the eligibility to file as a patent. That is called as patentability criteria. It can be explained by Nun's test. One is novel. Your work, whichever you wish to go for filing a patent, should be novel. It should have some utility, and it should have inventive step, or it should be non-obvious. And fourth one is it should be governed by statutes of the nation. So Nun's test is very, very important. Novel means it should be new. You should not disclose it to anyone until you file the patent. Utility means it should have industrial application in one or other industry. Either it may have direct application or indirect application, but it should be useful. And third one is non-obviousness. Suppose you have demonstrated something. By looking at that, I feel, oh, what is this? It is very well known. Even a small children can do it. Then certainly you will not get a patent. So therefore, there should be a non-obvious element or inventive step in your invention. And fourth one is, in spite of following these three criteria, even if your invention is, if it is not governed by any of these statutes, means you may not get a patent. So therefore, statutes of the patent is also very, very important, because each country has its own patent laws. Based on that, some of the works are patentable, and some works, though they are inventive, though they are novel, and though they have inventive step, even then they cannot be patentable. It is because the law is like that. And when we talk about Nun's test, this slide makes a lot of importance for all of us, because as a researcher, we try to show our work by way of presentation or by way of abstract, by way of poster or some other means. But however, if you are planning to file a patent, please don't do any of these things before you file the patent application. If you do any of these things, then your own things will constitute as prior art and you will not get a patent. So therefore, please don't disclose any of your research work either as a poster or as an abstract or as a paper or as a presentation to anyone until you file a patent application. Here, look at the example of a ring pull can. The inventor who has invented this could get 148,000 UK pounds as royalties per day during the validity of the patent. Validity of the patent is for 20 years. So every day he used to get this much money. That is the power of patent or power of intellectual property. Look at this. Michael Jackson has got a patent for his dancing pattern. That is the reason why there is no alternate for Michael Jackson. Look at this boy, Hridayeshwar Singh Bhati. He is the youngest inventor or patent holder from our country. So we should appreciate him. When a 9-year boy can get a patent, I think we all can get, because we all are more than 10 years. Yes. We all are more than 20 years even, or at least 18 to 19 years above. When a 9-year boy can get a patent, I think we all are capable of getting. The only difference is we have to orient ourselves toward that direction. If we can orient, then certainly we can contribute. Look at this. When you visit the American Patent Office, you can find this. The patent system added the fuel of interest to the fire of genius by Abraham Lincoln. Even Abraham Lincoln himself got a patent, US 6469, that is the patent number, and the title is Manner of Buying Vessels, which was issued to Abraham Lincoln on May 22, 1849. So that is how the developed nations are practicing. That is the reason why we call America as a super nation or superpower or developed nation or #1 country in the world. It is because of this. And here I try to show you some of the examples of patented inventions. A friction match that we use this is a very common household item in Indian societies, but this was not invented in India. It was invented and patented in US in the year 1836. Sieving machine was also patented in the year 1855 in US. He's a politician. Though he is a politician, he was also an inventor. He invented dishwasher. See, politician becoming an inventor, having a patent. Now in India, being a scientist or being a researcher or being a student, we are unable to file patents properly. But here a politician who is so busy, politician is always busy, whether in India or in other countries. Politician means they are busy. Even in spite of that busy, he could able to contribute. Which year? 1928 only. But now we are in almost all 2020 or 2021 now. No, none of our politicians or even none of us, we are really thinking to contribute for patents. So that is where we have to realize. Look at this. Traffic signal was invented in the year 1923. Even as on today, many cities don't have, many cities in India or many towns in India don't have traffic signal, and many people are dying because of the accidents, because of not following the proper traffic rules. But however, this was an invention, patented invention. For the countries where the population is very less, the traffic is even less, even then they have invented. Ballpoint pen, which was patented in the year 1888. I think we don't know, very recently we started using ballpoint pen on a regular basis. Otherwise in India, up to 1940s or 1950s, no ballpoint pen was there, only ink pen. So that is how there is a big difference in the technological development. Look at this, it's very funny. Chin rest for the dead. Hare, what is this? In India or in our communities, we don't have value for the living people, right? But in US, they give a lot of value to the dead people also. They have invented a chin rest. Whether the chin rest is there or not, how does it matter to that person who is already dead? But even then they have invented, they got a patent for that one. So that is the kind of development, that is the kind of exploration they made. Look at this. Steve Jobs has been awarded about 200 patents since his death. Whoa, this is again one more surprising slide, right? And I am still living. I could hardly get 5 or 6 patents, that too with lot of difficulty. This person is so crazy. Even after his death, he could get more than 200 patents. After, if we look for the same thing after 5 years, this number would have gone to 1,000. For us, even after 10 years also, the number will remain same. Even after 50 years also, almost the numbers will be same. So then, this is the time for us to realize. And this is the first patent from India from the year 1856. And this is the timeline for the patents. Today you file a patent. After 18 months, it will be published. After 24 months, it will be granted. And it will be valid for 20 years. And this is the first page of the first patent from India. First page of the first patent from India. He is the person penning and depenning. He started a company. Even now, his company is working very good. So we all have to appreciate him for his initiation. So he is the first person to get a patent, to get the first patent in India. And when we talk about importance, please look at this slide. There are more than 150 million patents as on today in the world. 80% of the scientific or technical information will be only present in the form of patents. That means whatever you get from your publication search or literature search is limiting to only 20%. 80%, we are not performing any search. We are not dwelling the literature because it is present in the patents. We are not aware of doing a patent search or looking at a patent or retrieving the information, because in our system it is that practice is not there. Since your faculties have taken initiation to conduct these kind of programs, at least now you are getting some kind of awareness. Otherwise, until I completed my PhD, I did not do any patent search. I have not even seen a single patent. With that itself, I could get my PhD, I could get all ranks, gold medals, everything. And on one side, I feel that I'm very great. But when I look into these aspects, we are very foolish. For very small things, we are feeling very happy. We are feeling very much great. But this is a big gap that is existing in our academic and research culture. That is where I think from last few years, the present system of education is insisting all the universities, research and academic institutes to come up with innovation councils or IPR cells, and they should have a policy, and they should also start some courses on IPR so that most of our learning can be oriented in this manner. The countries like China, US, Singapore, Japan, they teach the concepts of IPR from their school level onwards. Here in India,
Hello, sir.
Volume.
Hello.
Sir, this is Shankaran here. Dr. Pawan Kumar submitted has some issues.
I think I'm okay. So somehow there was some problem. Are slides visible now, or should I
think
share again?
Yes, sir. We have to share again.
Acha, I have to share again. Okay. Is it okay now?
Yes, sir.
Okay. So we'll finish in another 10 or 15 minutes. Okay. So this is the comparison. In 2008, the contribution from Asia was about 50%, whereas by 2018, it has increased to 66.8%. You know, this increase is not because of us. This increase is because of China. Look at this. These are the top 5 offices accounted for number of patents received worldwide. About 44% of the patents were filed by China, around 20% by US, 10% by Japan, 6.5% by Korea, and about 5% by European Union. All others contributing to 15%. That means India is nowhere. And if you see the statistics of India by population, we are number 2 in the world. By the area, we are number 7 in the world. But by patents, we feel that we are very intelligent. We have a lot of knowledge. We have a lot of tradition. Everything is there. But it is not reflecting here. That means there is some lack. A lacuna is there. So that gap we have to fill. These are the patent applications filed by different states in India. Maharashtra takes the lead, followed by Tamil Nadu, then Karnataka, then Delhi, Telangana, Uttar Pradesh, Andhra Pradesh, after Uttar Pradesh, Gujarat, West Bengal, Haryana, Kerala, and Andhra Pradesh. I think Andhra Pradesh in top 15 or top 12. But see, what is the population of Andhra Pradesh? Maybe about 5 to 6, maybe about 4 to 5 crores at least. What are the number of patent applications per year? 271. Huh? What is this? I think your own university might be having more than 300 faculty or researchers. If not your university, at least the universities like Andhra University or Usmania University, they may be having more than 500 or 600 people, active researchers. If every one of them files, the number will definitely go to thousands. But hardly that is 270. And most of these 270 is from industry people only, not from academics. Then, so this is how there is a very big gap in our culture or in our education and academic system itself. We did not realize the importance of IPR. Look at this, patent performances by India from different individual companies or institutes. Qualcomm, Samsung, Huawei, Ericsson, and Oppo. These are the top 5 players from foreign applications, and by applicants by India. That means people from Indian origin or Indian applications. IITs, all combined IITs are filing about 500. Chandigarh University itself is filing about 300 patents. Then TCS, then CSIR, then BHEL. So therefore, when we talk about Chandigarh University, a single university could able to file more than 300 patents. That means each and every university in India, there are about more than 900 universities. Each and every university in India is capable of filing more number of IPRs. But however, we have to be sensitized about that so that we can definitely contribute. And why is this? Why is that our performances are very, very poor? It is because of this. Please look at this slide. There are 200 times as many filings in Japan as in India per million population. Per million population, Japanese are filing 2,000 patents. USA and China and Germany are filing about 1,000 patents, whereas India is filing only 11 patents per million population. Similarly, we do have very less number of research scholars because per million population, Japan has about 500 research people. US has about 4,000. Sorry, not 500, it is 5,000. US and European Union have about 4,000. Even China has got about 200 researchers per million population. Whereas in India, there are only about 200 researchers per million population. In spite of this low number, we are very much struggling to find proper jobs or proper profession or proper work for the research communities. That is the reason why you can find many people continuing as postdocs for years together, because there is a need for the improvement in our system, which brings us lot of motivation to take up research so that we do contribute to effective IPRs. And when we talk about publications, I think this slide everyone might be aware of. We are top 3 in the world by number of publications. But if you look in top 1 and top 2, it is again China and US. So these two countries are top in patents as well as in publications. But we are top only in publications, but not in patents. Why is it so? It is because we are doing a following up research. We don't want to become leaders. We just want to follow someone else. That is the reason why we are ending up with only publications, but not the patents. Again, I think we could able to justify the reasons for this cover article. So therefore, research is to see what everybody else has seen and to think what nobody else has thought. That is what we have to do. But what we are doing is, if some publication comes in 20 impact journal, we try to follow it up and try to put it in 5 or 10 impact journal, so that we are very happy. By that way, we are remaining as following up researchers, not the true researchers or leadership researchers. So therefore, ideas are very common. We all can generate ideas, but inventions are rare. We have to tap this rarest part so that we can contribute to effective IPRs. And this statement is very, very, very correct for our working culture. Wisdom lies not in the amount of knowledge acquired, but in the degrees of its application. When we talk about India, we say that no, 1,000 years back in India, these things were known. 10,000 years back in India, all this technology was known. 3D was known, 3D printing was known, aeroplanes were known, surgery was known, everything was known in India some thousands of years back. Then what? Then if that is so, why is it that India is lagging behind in the global competition? Why is it that our performances are very poor? It is because, yes, we have wisdom, we have knowledge, we have acquired a lot of knowledge, but from last few decades or from last few hundreds of years, we could not able to convert this knowledge and wisdom into its applications. That is the reason why we are lagging behind with the other countries. That is the reason why we could not find a stand in the global technological scenario. So therefore, now we are in the age of invention. Whether you agree or not, whether you are interested or not, whether you will be happy or not, we have to contribute, because it is like do or die situation. If you don't do, then people will ignore. The whole world will ignore us. That is the reason why now a big boom has come in Indian research and academic communities. Everyone started talking about intellectual property, IPR, product, technology, do this, do that. So that is where even our Prime Minister in the recent Indian Science Congress of 2020, he has said these words: my motto for the young scientists in this country has been innovate, patent, produce, and prosper. Innovate, patent, produce, and prosper. These 4 steps will lead our country towards faster development. Yes, this is the time. If we don't catch up, then it is very difficult. Look at this. Even US, though it is #1 nation, they are sustaining, they could able to maintain its position because of their sustainable efforts. Innovation has been essential to our prosperity in the past, and it will be essential to our prosperity in the future. So that means they are putting their continued efforts. But we have to initiate, we have to propagate by ourselves, we have to perform, we should also try to excel. So these many objectives are there for us. Now, I have come back to the slide, the very first slide that I had shown it to you, but there is no question. All I asked was, can I patent my copyrighted trademark? Now, please let me know those who felt that there was no problem in that. Now you let me know whether you can find some problem or not. If you still find some problem, then you are on the right track. If you feel that there is no problem in this query, then again, we have to continue these kind of sessions for so many occasions so that we can come on to the right track. So therefore, innovation distinguishes between a leader and a follower. And everything starts with an idea. So therefore, we all should aim towards becoming a leader, not just the follower. This is the kind of inspiration that one has to develop. And here I'll show you some of the patented inventions which are from India, which have a combination of materials, engineering, and all these aspects, so that you all can understand. So these are some of the examples of patented inventions, the products which we are seeing in the market. Even these are some of the technologies that are developed by material scientists or material engineers, which are developed in India and are also licensed to industries, and they are in practical use in the market. So therefore, we need to have knowledge. Knowledge has to be added with experience. Then if we can add creativity to this, certainly we can convert most of our research activities into useful outcomes. And as such, when we talk about patents, prior art is global, patent rights are territorial. Similarly, science is global, technology is local. So therefore, in this direction, performing a patent search is very, very important. Whenever you take up any research activity, my advice is, before you select a topic, you try to perform literature search as well as patent search, where you can get more insights. So therefore, patent search is very, very important for all these aspects, to know the R&D developments, to draw the state of art, to identify geographical trends, and also to identify technological and research trends, and who are all the major players, who are all the major research institutes working in that area. You can make out. You can also find out the specific people or specific research groups working in those specific domains. And finally, you can also able to know the level of competition. Here I'll try to show you some of the slides. This is on nanomaterials, nanotechnology, and the percent contribution from different countries. And in all these slides, you find India in top 10, but however, not in top 3. Look at this. China and US. China and US are always there in top 1 and 2. Nanomaterials, nanoscience, and nanotechnology. And this is put together. Nanomaterials, nanoscience, and nanotechnology. So China is taking the lead, then US, then Russia, Europe, Japan, Korea. But however, India also finds a place in top 10. That means we are not really bad. We can pick up and we can certainly be in the competition, provided if we reorient ourselves towards this direction. So therefore, this is what we are lacking. Sometimes I feel most of our academic or research activities will happen in this manner, when we are physically present but mentally absent in the class. Maybe I may be wrong also, but that is what I felt. Now it is online sessions. Of course, this might be more applicable, but even in the offline sessions also, that is very common. We will be sitting, we will be present physically, but our mind goes here and there. Whether you do a classroom teaching or whether you attend a classroom or you are performing a research. So therefore, we should be very much attentive in the activities that we take up. And the second one is the teamwork. Somehow we are not really constructive in this attitude. Whenever we have to work as a team, somehow after few months or few weeks or few days, the team will split and clashes will come, that those works will not be taken forward. But the same thing is not happening in other countries. So therefore, always we have to be very much ready to take the risk. Risk drives the innovation. And we all are not the risk-taking people. We need credit. But when it comes to the risk part, we feel that, okay, this time leave it. No, it should not be our attitude. We should be ready to take up the risk. We should be ready to work as a team. And we should always be attentive to the activities, whatever we are performing. With that, I think we can definitely come up with effective contributions. And as an institutional level, whatever research you perform, try to screen them for the patentability possibility. Wherever you feel like there is a scope for patenting, try to apply for the patents. There are many agencies which support financially also, so that many of your works can go as patents. And for the same work, once you file a patent, you can also get a publication. It is like 1+1 offer. You will get a patent, you will also get a publication. And more essentially, we have seen many wars here and there, but in future, the wars will not be fought over territories, but they will be fought over ownership and exploitation of ideas. That is what is IPR, innovation, idea, creativity, everything is there. We have to apply that to the greatest level. Otherwise, we may not find our existence in the global scenario. And please look at this. If you are doing so, please let me know. Formulate hypothesis, accumulate data, do extensive testing. I think most of the research activities are oriented in this fashion. If it is so, then this is the old way. Then what should we do? Formulate a hypothesis, patent it, raise some $1 million. 17 is some number I am showing. Some dollars. You try to raise $1 million. That means your work should be capable of seeing the market phase. If not now, maybe in coming years. If that is so, then that is the new way of research. And this is what the way adopted by all the Western countries or most of the developed nations. That is the way, that is the reason why they are developing like anything. But it is the time for us to look into this direction. So therefore, a man may die, nations may rise and fall. but an idea lives on forever. So try to generate great ideas and become leaders. So these are the slides on different activities on IPR that we conduct, or I conduct. I conduct some training programs and teaching programs at UG, PG, and higher levels, and even for faculties. We do conduct some workshops for the faculties and also the interested inventors, and we do conduct some outreach programs. We have expertise in different databases for search and analytics, and I myself have drafted about 30-35 patents falling in the domains of chemical engineering, chemistry, biology, chemical biology, and even some patents in mechanochemistry. So with this, I think this is the slide where you have to comment on. I try to make my presentation on these pillars. It should be informative, impressive, effective, depictive, interactive, and whatever we discuss, I should try to show it to you so that you can believe. And finally, we should have some kind of relaxation. So with this, we have come to the end of our session. Thank you all for your patient hearing, and I hope I could able to justify the theme of your webinar, and I expect that some of you will definitely realize the importance of IPR, and as your Vice Chancellor and the Principal and HOD and other faculties have expected, you may come up with some of the productive contributions. Thank you all.
So thank you, sir. Pawan, sir.
Yeah, madam.
Really, today we have been enlightened about IPR with your elaborate
Thank you,
talk.
madam.
Really, it is very impressive. Thank you very much for being with us, sir, and not only motivating the academicians, but the young engineers, the young scientists, the budding engineers, not to stay back with their creativity, but to orient towards the innovation and make the secret trademark, patents, copyrights,
Yeah.
likewise. Really very informative, sir. Thank you very much. We'll be keeping in touch with you with your email ID and phone calls. Thank you, sir. Thank you very
Sure,
much
madam.
for
Thank
your
you.
time with us, sir. Thank you.
Thank you. Here, I would like to make one small note.
Yes.
What I suggest is, if possible, your university can have a course for all UG and PG and higher studies, starting from UG and higher studies, so that it can be a mandatory course like ISIS and many of other institutes are following. As an institution level, you can bring up that course, and also you can have some innovation council or IPR cell.
Sir, our engineering college is planning, sir.
That will certainly help in bringing a very good IP and innovation ecosystem in the university.
Okay, sir. Thank you. Yes, sir.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, madam.
Over to Vidya.
Thank you, sir, and thank you, ma'am. Now I would like to invite Dr. Bibi Ahmed Ali, Faculty of English, to propose vote of thanks.
Thank you, ma'am. I deem it a great honor to propose the vote of thanks to all who have helped us in making this webinar successful. First of all, I would like to propose our profound vote of thanks to Chief Guest Professor M. Jagannath Rao Garu, Honorable Vice Chancellor of Adikavi Nannaya University, for gracing today's webinar. I also take the opportunity to thank Registrar Professor T. Ashok for his guidance and support. Next, I would like to express our profound gratitude to today's resource persons, Dr. K.J. Shankaran and Dr. T. Pavan Kumar of CSIR Institute of Minerals and Materials Technology, Bhubaneswar, Odisha, for readily accepting our invitation and delivering wonderful sessions to our participants. I would like to extend our thanks to Dr. V. Persis, Principal, University College of Engineering, for her guidance and encouragement. I also would like to thank our course coordinator, Mr. M. Balakrishna, for his moral support and guidance. I am happy to express vote of thanks to the co-conveners and the organizing committee who have made this workshop a success. We are grateful to all the technical support team, non-teaching staff of University College of Engineering and Adikavi Nannaya University, as well as the press and media for covering this event. Finally, the participants from all over the college and the students, we thank you for your participation in making this webinar a fruitful endeavor. Once again, I thank you all for your cordial cooperation. Over to Vijay.
Thank you all for participating in this webinar and making it a great success. Thank you all.